Welcome back to Intro to Computer Vision. Today we're going to start a section that's really on mapping from across multiple images, image to images. And so I'll refer to it as N views. Mostly we're going to think about two views, but a lot of this stuff extends to having multiple views. Today what we're going to do is we're going to be talking about image to image projections. Because last time we talked about calibration, and calibration was all about going from the world to the image. And we made a stop. We go from the world 3D coordinate frame to a camera 3D coordinate frame, and then we do a projection from a 3D camera coordinate frame to a 2D image frame. And we built that M matrix, and we talked about if I gave you 3D points in the world and 2D points in the image, how you could figure out what that relationship is. For the next several lessons, we'll be talking about mapping from one image to the other. And this is going to be important both for stereo and for other applications where you have multiple views of the same scene. So here I have I think this is a figure from Forsyth and Ponce. Maybe it's from Sliski. I hope their lawyers aren't watching. It's somebody. And basically it talks about how you can transform an image. And so on the bottom left-hand corner you have a square, and you can see you could just translate it. They call it Euclidean, but that's just a rigid transformation where you have the rotation translation. You have similarity, affine, and projective. And we're going to talk about each of those in terms of the mathematics. So let's take the simplest example. So the simplest example here is translation. So we have an X, and by the way, in this cool little figure, sort of the original X and Y is the green box. And we take our X and we just add some translation vector to it. And we saw that it was an easy way to describe this using homogeneous coordinates, where we just do X, Y, and 1. We add a 1 to the end, and then we can just have a transformation matrix here, which is just made up of an identity plus the translation vector that we had from over here. And to keep the whole thing in homogeneous coordinates, we would just say, we would make instead of a 2 by 3, we would make this a 3 by 3, so that 0 vector now is on the bottom row, and what we would do is we get from one homogeneous vector to another. Okay? So that would be translation. By the way, because these are now just matrix multiplications, we could chain these transformations. So we also have talked about projective transformations. And remember for 3D we said that we used 4-length vectors and we had 4 by 4. Well, for 2D images it's just a 3 by 3 matrix applied to a homogeneous coordinates. So here I've written this as I have an original vector x, y, w, w being the homogeneous coordinate. I apply my 3 by 3, I get a new x prime, y prime, w prime, and of course to go to the non-homogeneous I have to divide through by the w prime later. So using this sort of general framework we can look at all of the transformations. So let's go back to translation. So translation in this framework is just the identity matrix up here, the translation there, the 0, 0, 1 there, and we go from x, y, 1 to x prime, y prime 1. In fact, we didn't have to do any division because we maintained that 1. And that's drawn with this cool little picture here where we just take this square and we can just translate it around. Nothing changes orientation, size. And translation preserves the lengths and areas of objects, so as I move them around, the angles stay the same, even the orientation stays the same, and because this is a projective transform, lines remain lines. And lines remaining lines is going to be key to everything we do for at least 5 lessons. Well, 4 or 5 lessons. All right, so that's translation. A rigid body transformation can be represented this way as well. It's called Euclidean or rigid body. And now, instead of having just a pure identity matrix, we have this rotation matrix. So we can rotate in the plane, and we can translate. So we have 3 degrees of freedom here. And again, we've maintained a rigid body, so lengths and areas are all preserved, angles are preserved, lines are preserved. But of course, the location and the orientation can change. Another one which people don't think of quite as much is what's called a similarity transform. In a similarity transform, we have translation here, the rotation by the thetas, and you'll notice everything is scaled by A. Okay, so that's an expansion, that's a scale. So there's translation, rotation, and scale. So how many degrees of freedom of that? 4, right? 2 for translation, a rotation, and a scale. Now, one that we use actually a modest amount in computer vision is what's referred to as an affine transform. Okay, and an affine transform, you'll see that we have 6 degrees of freedom here, and I've just written them as a linear transformation, A, B, C, D, E, F. Okay? And again, we go from xy1 to x prime y prime 1. And what an affine transformation can do is essentially map, and we'll look at this later, any 3 points to any other 3 points. All right? And what you do is you're essentially now being able to translate, rotate, scale, and skew the image. And there's skew in both directions, so there's 6 degrees of freedom. You still maintain parallel lines, so the edges of this square become the edges of a parallelogram, okay? And ratios of areas remain the same. So if I had one area here that was half the size of the area to the left, then its transformation would be half the size over here. But the area itself can change right through scaling, all right? And again, lines are mapped to lines. Notice that we don't have to do the division still. Remember, these are homogeneous coordinates. So here I wrote it instead of with W, but with S's, right? So it's full homogeneous coordinate system, which will go from the homogeneous xy1 through a linear operation to a scaled version of the new x prime y prime, all right? So the full transformation is referred to as a general projective transformation or a homography. And a homography still maps lines to lines, because remember we talked about perspective transforms always maintain lines. And things that are inside of each other stay inside of each other. But this is what's typically sometimes referred to as perspective transform, right? So the idea is if I had a plane and I was very close to you and I tilted it this way, and we'll do more of this later, the edge that's near you will seem longer than the edge that's farther away from you. And we'll prove later that the transformation of a plane can be represented this way. Now, of course, because this is a homogeneous transform, I can scale everything by a constant and it has no impact. So I can make this last degree of freedom be a 1, right? And I'll get a slightly different W, but it doesn't matter because I'm going to divide everything through by W anyway. So that 8 degrees of freedom, that's the full homography. It's referred to as the homography. Now I want to do a little series of quizzes that relate essentially the transformations to points. So here's quiz number 1. Suppose I told you the transformation from image A to image B is a pure translation. How many pairs of corresponding points would you need to know to compute the transformation? So I say pairs of points, meaning pairs of corresponding points, meaning I've got a point in A and a point in B, and that's a single pair of corresponding points. So the question is, how many pairs would I need in order to figure out the translation? A3, B1, C2, D4. All right, well, the answer is B, 1 point. Because translation is a 1-point transformation. If you tell me where this bottom left-hand corner, better make it bigger, big point, bottom left-hand corner is over here, I know where the rest of the image goes. A couple of ways of thinking about that. One to think about is there's only 2 unknowns. And every pair of corresponding points gives me 2 equations. It tells me how the 2 x's align and the 2 y's align. So each pair of points gives me 2 equations. I have 2 unknowns, so I only need 1 pair of points. Got it? Cool. Quiz 2. 2. My finger's a little slow. 2. Suppose I told you that the transformation from image A to image B is affine. Okay, now you have to go back through a few slides. Remember what affine is. Go ahead. Okay. How many pairs of corresponding points would you need to compute the affine transformation? Same set of answers. A, 3, B, 1, C, 2, D, 4. How many pairs of corresponding points to do the affine? Well, the answer is A. I had to go back and see, because it's a 3-point transformation. And as written here, there are 6 unknowns in the affine transform. Okay, it's linear. Each pair of points gives me 2 equations. I need 3 pairs of points, which is what we said before. I could take these 3 points and know where these are, and then everything follows from that. Suppose I told you the transform from image A to image B is a homography. Homography. Your word processor probably doesn't know about homography. Mine didn't. It keeps changing it to photography and other things. Homography. How many pairs of corresponding points would you need to be able to compute the transformation? Same set of answers. A3, B1, C2, D4. How many points? Well, the answer is 4, which is D. All right? Why? Because we have, well, wait a minute. It looks like 9 unknowns, right? It's 3 by 3. But no, you've seen this before. It's only matters up to a scale factor, right? I can scale all those entries in the matrix by a constant, and when I map it back out to the non-homogeneous coordinates, when I divide it out, that scale factor goes away. So there are 8 unknowns, 8 degrees of freedom. Again, I can take 4 points, the 4 points of a rectangle, plop them down here. They don't have to be 4 points of a rectangle, it's just easier to see. And once I've mapped 4 points to 4 points, assuming I don't have any weird degeneracies, then I could compute the homography. What do I mean about weird degeneracies? Well, here would be one. We said that points that start on a line have to stay on a line. So if I took 4 points that were on a line, and then I mapped them to 4 new points that were not on the line, the system should explode, and it would, and your computer would melt and all that kind of stuff, because there is no linear solution of this projection that would map 4 collinear points into 4 non-collinear points. But in general, if I have 4 points distributed spatially, and I put them down, and I map them to 4 other points distributed spatially, then I'm able to compute the homography. Many times through this class, I'm going to ask you, how many points do you need to compute a homography? And I hope at least you'll scream 4. I'm amazed when I do this in class. I say, how many points do you need to do homography? And they don't know, and it's only been like 8 minutes since I did this, so pay attention. Believe it or not, that's the end of this lesson about mapping from image to image. It's a short lesson. I know I needed a break, or you needed a break, or somebody needed a break. Anyway, what was happening was I had these lessons, and they were going on for like 12 hours. And I said, that's probably not good. So in the interest of bio breaks everywhere, we decided that we would shorten some of these. So that ends on sort of image-to-image transformation using the projective transforms. And now we're going to continue our conversation about projective geometry. And it'll get a little bumpy, so, take a breath, we'll charge ahead. The cool thing is, the next thing we're going to do is make serious use of homographies to do something cool that will wow and amaze your friends, assuming you have relatively nerdy and boring friends. Otherwise, they're going to tell you to get out a little bit more often. Anyway, talk to you soon. Welcome back. All right, so today we continue on our tour through multiple views and views. And today we're going to talk about homographies, which we learned a little bit about last time, and a cool thing, mosaics. In particular, last time we talked about a variety of projective transformations. We said there were some special cases like translation similarity that did not divide out by that last time. But in the general case had 8 degrees of freedom, 8 coefficients, and you did do that division to go from homogeneous to inhomogeneous. And that last one, the one that used all 8, was called a homography, and we're going to use that extensively today. This was the description of projective transformations. For 2D coordinates, it's 3 by 3 applied to the homogeneous, so x, y, w gets mapped to w prime x prime, w prime y prime, w prime, and to go to non-homogeneous or inhomogeneous, you divide through by the w. So now I'm going to do just a little bit of the projective geometry that relates to the homogeneous coordinates we've been talking about, and we'll do that a lot more in the next lesson. So what is the geometric intuition behind using homogeneous coordinates? The bottom line is that a point in the image can be thought of as a ray in projective space. So what I mean by that is, so every point x, y on the image plane, let's change the color here so you can see this. So here we have this point, and we're talking about x, y, can be thought of as on this ray intersecting an image plane that's at a value of z equal to 1. By the way, and I stole this slide from someone, somebody was very clever here. They wanted positive z to go along the direction of the camera. So you notice they have x this way. This is negative y. So it means positive y is down, and if x to the right and positive y is down, x to y means z goes that way. It was a way of keeping a right-handed coordinate system. Don't worry, you will screw this up. That's okay. In case somebody saw the picture and wondering why it said that, that's what it is. Back to our regularly scheduled program. All right. So if this point on the image, xy1, is just this ray intersecting the image plane, that means that any point along that ray is on that, it projects to the same point in the image plane, and the points along that ray are the scaled SX, SY, and S, if you multiply by scale factor. And remember, in homogeneous coordinates, SX, SY, and S, you divide by the S to get out the new X, the new Y. That's the relationship between that homogeneous transformation, dividing out by the third coordinate, and this notion that a point on an image is essentially equivalent to a ray in space coming from the center of projection and intersecting the image plane. We're going to make way more use of that in our conversation next time. We're only going to use it a little bit this time. So given that little bit of information, we can now talk about image reprojection. Here's the basic question. How do we relate two images, so I have two images, projective plane 1, projective plane 2, where the center of projection of the camera was the same? Okay, so I've got the camera and its center of projection is fixed, and I take two images. So the question is, how do I map from projective plane 1 to projective plane 2? Well, here's the answer. Basically, think of that image, or the point on the image, as we said, is it's actually a ray in space. And it's a ray from the center of projection through the image plane, intersecting the image plane. And then in order to figure out how to map from projective plane 1 to projective plane 2, I basically have to figure out where that same ray intersects projective plane 2. So if I knew where that plane was, then I could just figure out where that point is. All right? And so that would be, right here. Okay? So what should be clear is that in order to figure out where this ray was intersecting projective plane 2, I didn't actually have to know where in the world that ray hit. I just need to know the camera center, the location of the point in image plane 1, that defines the ray, and then I intersect the ray with projective plane 2. Where it hits in the world is irrelevant. What that means is, instead of thinking of this as a reprojection from 3D to 2D and figuring out how it projects to some other 2D plane, when I'm going from two planes that are from the same center, I really want to think of this as a 2D image transformation. A 2D, it says here, image warp from one image plane to the other. I don't have to worry about the third dimension, the 3D world. So a very cool application of this is what's referred to as image mosaics, or sometimes called image panoramas. So would you like to know how to make an image panorama, sometimes called an image mosaic, which is way easier to say than Panama? Maybe they make them in Panama. I don't know. We're going to make panoramas, and we're going to use homographies to do this. All right, so here's the basic procedure of how to make a panorama. You're going to take a sequence of images from the same position. So you might ask, well, if it's from the same position, don't I get the same picture? No, you're going to rotate the camera about its optical center. So the position stays the same, but the direction that the camera is pointing can change. Then what you're going to do is you compute a transform between the second image and the first, or the first and the second. And then what you do is you transform that second image to overlap with the first according to the correct transformation. And then what you have to do is you have to blend those two pictures together to make the mosaic. And of course, if there are more images, then you have to repeat. But wait a minute. How come I don't have to worry about the 3D world in order to put together a panorama of images that are taken of this whole big world that's got different depths, etc.? What about the 3D geometry of the scene? Why aren't we using it? Well, you can probably guess it's that thing that we said before about that when you're projecting from one image plane to the next, if they're taken from the same camera center, the 3D world is irrelevant. So I don't actually have to know the scene structure in order to paste together these pictures to make a panorama. So there's a cool way of thinking about image reprojection, sort of a natural geometry. The first is take one picture, another picture, and you'll see here that all of these pictures were taken by rotating my camera, and I've drawn it as if the camera's center projection was perfectly aligned. Of course, it's never perfectly, but pretty close. Although you can buy little tripods that make it easy to rotate the camera right above the focal point of the lens. In fact, if some of you have a really good camera, it'll show you where the film plane or the sensor plane of the camera is, and then if you know the focal length of your camera, of your lens, sorry, let's suppose it's a 50 millimeter lens, you would measure 50 millimeters from that point, and you know that's the focal point of my lens, and you could set your tripod up so that the axis of rotation is right underneath that, and that's how you'd actually do that rotation. So anyway, so we show here that we have three images taken from three different orientations. Then what we want is we're going to project all of these images onto some single mosaic projective plane. All right? So here we're showing projecting image 1, projecting image 2, and projecting image 3. All right? And so the idea is that you're projecting everything down onto a common plane. And of course there is some overlap, which is actually a good thing, because in order to figure this out, you're going to need overlap. But of course, you're also going to have to figure out, A, how to transform these images, and B, how to blend them. So this is way of thinking of mosaics is that these are images that are reprojected on a common plane, and the mosaic is formed on that plane. Before we go further, this only works for sort of a limited field of view. But you might be thinking to yourself, wait a minute, can I take pictures all day spinning around on my tripod? Now you get to see how much hair I don't have on the back of my head. I know you've always wondered about this. Anyway, it feels like you should be able to paste together pictures going all the way around. And you can. And in fact, Photoshop and even little cameras that you buy do this for you. They're not actually projecting it onto a plane. They're projecting it onto some other surface like a cylinder. And then you unwrap the cylinder and you get a panorama. It turns out that's not actually a real picture. It's sort of a, I mean, it's a real picture, it's made up, but it's not a particular scene. Whereas when you do a panorama onto a plane, it's as if you had a super wide field of view camera. So it's two different kinds of things. When you do the really wide ones, it maps it onto a cylinder. So how are we going to do this? All right, so here's an example, again, courtesy of Steve Seitz. So what we're going to do is we're going to take these multiple pictures. These are from the Great Wall of China. Thank you, Steve. And, you know, what's drawn here is this idea that we've taken all of these pictures from the same center of projection. So how do we do this? Well, as we talked about before, the projection between two planes, shown here as P prime equals HP, is just a homography. Remember that from last time? A homography that allows us to map from one plane to the next. In fact, a little bit later, I'm going to show you a nice little proof that says a projective mapping between any two planes can be represented as a homography. But here we've represented it as just H, going from one set of points to another. So let's now compute this homography for the Great Wall of China. Actually, Steve did this a really long time ago, but I'm going to pretend that we're doing it right now. So in order to compute the homography, the first thing we need is we need sets of corresponding points, all right? So on the left, we have the original points, x1, y1, x2, y2, all the way up to xn, yn. We have a bunch of points. And on the right, we have the corresponding points in the second image, x1 prime, y1 prime, x2. And for now, we're going to assume that these points have been found by that tried and true method of paying somebody else to click on them. That's called Amazon Mechanical Turk, or something where, or maybe you're an undergraduate and your advisor is beating you up and so you have to do all the clicking. Or maybe you're doing this for a problem set for a computer vision class and you have to do the clicking. But basically the idea is somehow you've identified corresponding points between the two images. So what we have to do now is we have to solve for this equation, right? We know that the relationship between P and P prime is going to be this homogeneous coordinate transform, or homogeneous homography H. So how do we solve for H given some number of points? Well, there are two ways. The first way is the non-homogeneous, boo hiss, all right? Going back here, even though there are 9 variables in the matrix, we know there are only 8 degrees of freedom because it's only known up to a scale value. So we can set, for example, the last entry to 1. All right? Well, then we can set up a linear set of equations, AH equals B, where the vector now is of H, where it's going to be A, B, C, D, E, F, G, H. But this H isn't the same as that H. This is the H that's all the elements of the big matrix H, and this is dumb little h. Okay, so we got A through F, pretty smart, and dumb little h. And then G's in there somewhere. You get it. There's 8 unknowns. Okay, if I knew the first 8 letters of the Greek alphabet, I would have made them that way. But basically, I've got 8 unknowns. As long as I have 4 points, I would have 8 equations. Why? Because I get an equation for the x and an equation for the y for each point, corresponding points. But I really, because my locating of the points won't be precise, I would be better if I had a whole bunch more points, and then I would do a least squares solution. And you would solve for the minimum of the magnitude of AH minus B squared, the minimum of that square, using least squares. And you've known how to do that since 8th grade, I hope. 9th grade, 12th grade, I don't know, somewhere along the way. If you don't know what I'm talking about, go learn a lot of linear algebra before we take the rest of this class. All right, but this is the non-homogeneous way. Thinking about this set of equations, we've already seen this, right? Remember when we were doing the extrinsics, and we had a whole bunch of equations, 2n of them, and we had am equals 0, because we didn't change it. So we can do just like we did before. You multiply this through, you divide out by w, and you'll get 2 homogeneous equations for each point. Right? Now instead of m, we're solving for h, and we have a whole bunch of terms, all linear in terms of h, and it equals 0. And we have 2n of those equations, where n is the number of points. And how do we solve this? We'll use that singular value decomposition just like we did last time. Or you could take that A transpose A matrix, solve for the eigenvectors, pull out the eigenvector with the smallest eigenvalue, and that was our solution. Remember, we showed that it was the same thing. That's the way for solving for the homography coefficients. And by the way, that's the cool way, because you can impress people, because you can tell them you use singular value decomposition, which has so many syllables in it, they're sure you're really smart. Once we've solved for the homography, we have to be able to apply it. So what apply it means here is I might have some point in image 1, some point at x, y, and using the homography, I can pump it through, get the x prime, y prime, w prime, divide through by w, and I get the new x prime, y prime. That tells me the location. And I have to essentially transform that first image to the second image by moving that point to that location. And I could do that for every point in the left image, and I would have transformed it to the location of the points in the right image. By the way, we sometimes refer to this transforming of the image as warping the image. In fact, we're going to talk about how you do image warps in a little bit, image warps. It's actually going to be interpolation, but that's giving away the secret. All right. So once you do that, you can take, for example, these 4 pictures of the Great Wall of China, and you can wave your magic computer vision wand, and voila, out comes what looks like a spectacular wide-angle view of the Great Wall of China. Thank you, Steve Seitz. Now, you'll notice that there are some distortions here, and one of the things I want to point out to you is that there were some distortions in the original image. Like you see here, some of the lines are bent. That's to do with distortion on some of the lenses. But in general, lines stay lines when you project them onto planes. And that's a pretty cool picture. There are other applications of essentially mosaicing pictures together. Here's one that was used for, the comment is content-based coding, which is stolen from somebody who stole it from somebody who stole it from somebody else who's now lost forever. But basically the idea here was, what we do is we have this tennis player, and you can see the tennis player is being removed. And the way that was done is you essentially take all of the pictures, and it's a camera, TV camera, that's rotating about its focal point, so you can line up the pictures. Now, of course, they line up pretty well everywhere except where the player is, and so you can use a particular method called ransack, which we'll talk about, I don't know, probably 9 years from now, to figure out what the most likely relationship is between each of the pictures, line them up, and anywhere that the pixels have changed a lot, you say, I'm going to throw that away, subtract that out, and that removes the player that's moving around, and what you get out is this nice big background, which is as if you had this really wide field of view, okay? And then if you wanted to have the player running around on this background, you could just play the player moving around on this different background. Lots of people have used these types of mosaics in order to be able to show you cars traveling on a really big area, so it's taken from an airplane with a narrow field of view, but it sweeps across, and it's basically building up this big background to do what's referred to as content-based manipulation, content-based coding. Okay, time for a quiz. Simple quiz. You're going to love this one. We said the transformation between two images taken from the same center of projection is a homography H. How many pairs of corresponding points do I need to compute H? A, 6, B, 4, C, 2, D, 8. Right? And everybody's going to say 8 because it's 8 degrees of freedom. No, it's 4. It's 4 pairs of points. Each pair of corresponding point gives you 2 equations. So you'll remember that. There are 2 more things I want to show you. One is just some nice little mathematics to explain to you about homographies and planes. And the second is some of the cool things we can do with homographies and planes besides just mosaics. So let me show you a simple proof, if you will, or demonstration about this 8 degrees of freedom being a mapping between any planes. So let's go back to our calibration from the external world to the internal world. So you remember this? Right, XYZ1 is mapped through a 3 by 4 homogeneous matrix, or I should say it's a matrix, but we're doing this homogeneously, to get out the projectively similar UV1 over there. And remember we talked about solving for all the 12 M's using lots of extrinsic points. But suppose, just suppose, all the points in the world were lying on a plane. So you might remember from your algebra that simple equation of the plane, AX plus BY plus CZ equals D. Right? So that's the equation of a plane. Basically what it says is it gives me the normal to the plane and where along that normal the plane has to be. What this equation means is that I could solve for Z in terms of X and Y and A, B, C, and D, and I could plug that in. And that's what we did here. Here we removed Z and put in its equivalent expression in terms of X, Y, and then the A, B, C, and D, which define the plane. And so now it's the same M matrix that we had before, but we've gotten rid of the Z. But wait, if I have only X, Y, and a constant in this term for Z, I can put all the influence of this column, 0, 2, 1, 2, and 2, 2 of M, I can put that in these other coefficients. Right? I don't actually need this column since that's just multiplying the terms that have the x, y's, and the constants in them. I can put all the effect into those other 3 columns. So when I do that, it looks like this. Okay? And you'll notice I now have a column of zeros here. Okay? So that's really not doing very much. I just have these 3 columns multiplying x, y, and 1. All right? But that's just a 3 by 3. That's my homography, okay? That's why the mapping from any plane to any plane can be done by a 3 by 3 from a location on one plane to a location on the image plane, and so basically between any planes. In fact, a way of thinking about that is this, right? Mapping between planes is homography. You give me 4 points on this plane and 4 points on that plane. I now know how all the other points on the plane map to each other. And whether it's between a plane in the world and an image plane or just thinking about it between arbitrary planes, that's the warping that it takes in order to do this homography or projective projection warp between the planes. And mapping between planes is something we do a lot in computer vision, which is why these homographies show up quite a bit. We're going to do even more sort of sophisticated way of thinking about lines and planes in the next lecture, where we do even more about projective geometry. Got it? Cool. What else can we do? Well, if I can warp between planes, arbitrary planes, that means that I can take planes that, say, are in some particular orientation and think about what would they look like turned in a different orientation. So here we have a situation where we've got a plane. It's the side of this building. I'm going to assume the building is more or less planar. And I'd like to rectify that. That is, I want to remove the slant. So you see this window here? All right, you see how if I were to extend out, these are vanishing point lines. All right, so these are not parallel. They're going to converge. You can see that here. They'll converge all the way out there. All right. But if it was frontal parallel, then they would remain as parallel lines. Well, if we could compute the relationship between this quadrilateral, which is essentially like a trapezoid, between that and a rectangle, we would be able to rectify the entire building. And in fact, that would look like this. At which point you're supposed to say, ooh, that's cool.
Ooh, that's cool.
Very good. So here's the corrected image where now everything is rectilinear. And in fact, if you take a look at these windows, in fact, notice that these are sort of narrow windows here and wide windows here and narrow windows there. if you want to think about that from a measurement perspective, you can see that the windows that are sort of 2 panes wide were narrower than the ones that are 3 panes wide, even though clearly this is wider than this in the image, but when I rectified it, I was able to measure the whole thing. Show you another example of that. So here's a picture. Suppose you want to measure something, let's say start with on the floor, okay, so something about across what's on the floor. Well, they have tiles, and those tiles are actually rectangles. So I could unwarp this picture so that those tiles are now squares, because they're, let's say, 9 by 9 inch squares, which is some number of centimeters. 9 times 2.54, say 18 to 4, I don't know, 23, 24 centimeters. Anyway, I can rectify that image, and then I could go ahead and I could measure in that new image directly about the tiles. Likewise, if I wanted to measure something on the side of this wall, and that's a planar surface also, it happens to be very skewed, I could rectify that. And here, I've taken that wall and I've spread it back out to being rectangular. Actually, I didn't. The person I stole the slide from did. And I could now measure on that. And what kind of warp is this? What kind of transformation? Plane to a plane? That's right. It's your friend, the homography. Just to show you what I was talking about from not from quadrilaterals to rectangles, here on the left-hand side, I've identified 4 points. And you can see those 4 points are the 4 corners of a 2 by 2 tile matrix, but of course the points aren't rectangular because of perspective foreshortening, right? But I can warp that to being a regular square or rectangle, and the rest of the image will come along for the ride. Turns out that there are some other rectangular grids. It's really nice when somebody spray paints the rectangular grid. Here you're seeing a movie of a American football play. In fact, this is a college football play. But you'll notice they're running around on a plane, because to play football on bumpy things is hard. All right? So since it's a plane, we can rectify that to a different plane. In particular, what about the plane that you would see if you're looking sort of overhead? Okay? So what we've done is, this is just the same frame mapped to a different view where we've taken these lines which converge and we've made them all parallel. All right? Now you'll notice all the points go to the right place, except the players, of course, right? They are not on a plane. Just their feet are on the plane. So the feet go to the right place, but the players themselves are stretched out, because the players are not on the plane. But what we did is we applied the entire homography, we applied the homography to the entire image, so everything on the football field went to the right place, the players went to a slightly different place. But you'll notice, if you look at this, you could see exactly what's going on. Here you see 2 videos playing at the same time. One is the play as observed by the camera. The other one is this rectified thing. A little bit of shaking is going on here because this was done all automatically. And by the way, this is like one of the few results I'll show you that was actually done by a student of mine when we were doing about interpreting American football plays, and this was just a pre-processing step. But we're able to recover the projection. So if you need to save money on a blimp, this is what you do, so you can see an overhead view. In fact, in some sense, this is easier because you see the side of the players, not just their overhead. So I probably should have patented this and made $1 billion, and then well, it didn't happen. We've kept talking about warping images from one to another. That is, we take an image, we pump it through, is the phrase I've been using, or we transform it by homography, which means we have to go and transform this image. We have to warp this image. So the question is, how do we do that? The answer is there are 2 ways, the forward and backward. And there's another word for those, the wrong way and the right way. Image warping can be thought of this way. Suppose I have an image transformation, and I have some source image, f of x, y, and I know how that maps to x prime, y prime. Or another way of thinking of it, I know how that maps in the other image. I'm going to create some new image g, and for every x prime, y prime in it, or call it a and b or ij, what value should go there? And this t of xy is the transformation that says, given xy in one image, that value should go to x prime, y prime in the second image. So forward warping works as follows. You basically send every pixel f of xy, so I've got the first image, it's at xy, I send it to its corresponding location in the second image. So I have some pixel here, a little red dot, I know where it goes, and I put that same color that was down on the first image down in the second image. And that's okay, but you might ask the question, well, what happens if this pixel lands between pixels in the new image? Let's take a look at that. So here's a picture, and I credit Alyosha Efros about this. And in this picture, let's assume that the lines are exactly, y equal 2, y equals 3, and x equals 14, and x equals 15. So the intersections of the lines are the precise pixels. So if I have a pixel here, and I map it across, I may land somewhere between a pixel, okay? And somehow what I have to do is I have to take the color that came from this location, and I have to distribute it among all the pixels that are around where I landed. In graphics, that's known as splatting. That's the technical term. I mean, I guess it's the idea if you threw some paint down there and all the paint had to drain out to its neighbors, where would that paint all land? And that's sort of an annoying way of doing things, and that's why I said that that was the wrong way of doing warping. The right way is what's known as inverse warping. Given some pixel in x prime, y prime in the new place, transform back, figure out where it came from. So now xy is the inverse, t inverse of x prime, y prime in the first image, right? So I have to figure out where it came from. So I have a pixel on the right, I figure out where it came from in the left. Now you have a different question to ask. You no longer ask question, what happens if I get sent to a location between pixels? I now have to ask the question, okay, what happens if a pixel comes from between two pixels? Well, what you have to do is what's referred to as interpolation. Interpolation basically says, if I have some set of pixels, and I'll think of them as being at integer locations, so I have some pixels here at the corner, and I wrote that as ij, I plus 1j, ij plus 1, and I plus 1j plus 1. So those are the corners. If I want to find the value of something that is, say, a distance in x between the two pixels, and b distance or b percentage in y between the two pixels, what's the value? The general process of determining what the value of a function should be between points that you know is referred to as interpolation. Here we're back to thinking of our images as functions a little bit. So we have a value of the function at each of those integer locations, and we need to guess the value of the function at this location that's somewhere between the points we know. That general process is referred to as interpolation. The simplest interpolation is called nearest neighbor. Nearest neighbor means, well, just like it sounds. I land someplace in my grid, and I say, oh, you're the closest value. I'm just going to pretend that I'm that value. So this quadrant would all have one value. This quadrant would have another value, etc. It's not a very clever, not a very smooth way of doing things. A much better way, and perhaps the simplest computational way, is called bilinear interpolation. Bilinear interpolation basically says that I figure out the value in the x direction along both the top and the bottom, and I do that by linearly interpolating between those two values, and then I would interpolate between those values again using a different proportion, in this case b. Because these are all linear operations, you can just write it as one single linear operation, and you get this formula here. And it's very clean and very easy. There are more clever ways, bicubic, where you take, instead of just fitting linear things, you fit cubic splines between them. But basically the idea is that you're interpolating. And what's nice now is that you don't have any holes in your picture, right? You went for every pixel in the target image, figure out where it came from in your source image, interpolate that value, and stick it in the target image. So there are no holes in your warped target. By the way, it won't surprise you that MATLAB and OpenCV and Octave and all these supports this interpolation generically. In MATLAB, you can take a look at this function called interp2. That's two-dimensional interpolation, and it will allow you to do this. All right, so just to review a little bit, we talked about sort of a practical application about how to make a mosaic or a panorama. We said you take a bunch of pictures from the same center of projection, same camera position. You compute the transformation between each of the images, say the first and second, right? What's that transformation going to be? Well, same center of projection is going to be homography. You then use that homography to transform, say, the first image to align with the second. There'll be some overlap, so you'll have to blend them, and then you can continue to do that. So that was sort of the cool application. But the theory, and this is a really important part, is that homographies map from planes to planes. And this allows us to compute what a different image plane would look like from the same center of projection. So we can build mosaics by projecting a set of images that are all taken from the same camera center. And in general, what we're doing is we're working more in this projective relationship between image planes. So that ends the lesson on homographies and mosaics. That was kind of the cool part with a very gentle introduction to projective geometry. Now we're going to do a little bit more serious, or next lesson I'd say, we're going to do a little more serious conversation about projective geometry and the duality between points and lines. How often do you get to use the word duality at a party? I mean, seriously. We're going to talk about the duality between points and lines, and that will help us get to the relationship between sort of arbitrary cameras that you might, I don't know, want to do stereo matching between, or some other alignment between those views. Welcome back to Intro to Computer Vision. The last time we talked about homogeneous transforms and said how they were a form of a projective transform. And we showed for how homographies are your best friend. They allow you to map from one plane to another and to be able to map image planes, and that allowed us to do panoramas and other kinds of cool things. Today what we're going to do is we're going to get a little heavier in the projective geometry stuff. It's actually a short lesson, and we're doing this for three reasons. One is no self-respecting computer vision person should not know something about projective geometry. So you can say you know something about projective geometry and impress your parents. More importantly, or maybe significant others if you're dating a nerd. More importantly, we're going to use them a little bit when we talk about the relationship between multiple views, because projective geometry is just a very convenient way of representing the projection operator, which after all is how images are made. All right, so why projective geometry? And we're going to show you some of the math. All right, so what is the geometric intuition of using homogeneous coordinates? Well, basically, the idea is that we're going from a ray in space is mapped to a point in the image. So here you see a ray that intersects the image plane at z equals 1. And the idea is that every point xy, so every point xy on the image plane at z equals 1 is represented by this ray. So you see this ray here, right? And it intersects the image plane at xy1, but any point on this ray, sx, sy, s, would intersect the, when projected through the center of projection, would intersect the image plane at the same location. And that's what it means to be projectively similar. Okay, and that's the relationship between sort of these rays and the points in the image. So we already know about sort of going between homogeneous coordinates and regular coordinates. So in 2D, for example, we take a 2D point, xy, to make it homogeneous. We just add a 1 to it and become a homogeneous coordinate. That last coordinate can be thought of as the thing that tells you about the scale. So when you go from homogeneous coordinates to regular, you just divide by that scale value. That's what's shown here. But homogeneous coordinates actually allow us to do a lot more. In particular, they're going to give us a natural way of thinking about lines. And this time we mean two-dimensional lines. So here we have our standard equation for a two-dimensional line, ax plus by plus c equals 0. And what's nice is in homogeneous coordinates, it can be thought of as just this dot product essentially, right? It's ABC transpose times xy1, or I should say multiplied by xy1. And when you think of the line that way, A, B, and C can just be thought of as being the component of the unit vector in the direction of the normal between the origin and the line, and then every point on that line, when you dot it with that normal, has to be a distance d away, so that would be minus d. But the thing to think about also is it's saying that the normal, ABC, is perpendicular to the point xy1, or to the ray that defines xy1. So what's this deal having to do with perpendicularity? Get that out in one word, all right? And in fact, this perpendicular relationship is key to using projective geometry to define our points and lines. So to understand this perpendicular relationship, let's look at the projective space. So what does a line in the image correspond to in projective space? Well, a line really is defined by this plane of rays that's intersecting the image plane, and that plane is defined, like all planes are, by a normal. And this is that same normal, ABC. So all the rays that are perpendicular to that normal form the line, because the line is really just a plane in this projective space intersecting the image plane. Cool, right? It gets better. Oh, and we can write this very simply in the same vector notation I was showing you before. So it's essentially, in fact, you know what, let's say L transpose P if I wanted to write it that way, right? So that's in vector notation. And the thing to think about is that in projective geometry and in this homogeneous coordinate system, a line is also a homogeneous 3-vector. So a point is a homogeneous 3-vector, but a line is also a homogeneous 3-vector. In fact, this relationship that a point is a 3-vector and a line is a 3-vector is what's going to get to this duality between points and lines. And as we said, a line is a homogeneous 3-vector, which is defined by that normal to the plane, and it is perpendicular to every point P that's on that plane. And what does it mean to be perpendicular to a point? Well, in projective geometry, being perpendicular to a point means that you're actually perpendicular to the ray that defines that point. And that's what gives us some of that duality. Given these points and lines are both 3 vectors and we have this duality, suppose I have 2 points, P1 and P2. Now remember, points are actually these rays, P1 and P2. How would you solve for the line that goes between them? Okay, so you know in algebra, if I gave you 2 points, you would figure out your formula for line. Well, in projective geometry, it's actually pretty easy. Since L here is just perpendicular to both P1 and P2, well, you remember how to get a perpendicular vector given 2 other vectors. You just take their cross product. Okay, so L is equal to P1 cross P2. That's it, no problem. Okay, and L is the normal to the plane. So that plane is the line, so the way I get the line is I just cross the 2 points. Very easy. Let's keep going. What is the intersection of 2 lines? Okay, so remember now, I've got a line L1 and L2, and remember that they're actually planes, and what I'm showing you here are the lines that are made up of the planes, where the planes intersect the image plane. So the L1 plane gives you this, the L2 plane gives you that. Okay, well, just a little bit of thinking here, and you realize if the point P is perpendicular to L1, and point P is perpendicular to L2, okay, then what I need is a line that is perpendicular, or I need a point whose ray is perpendicular to L1 and L2. All right? Well, that's easy. So just as we had before, in order to find the intersection, in order to find the line that spans the 2 points, we took their cross product to find the line. In order to find the point that's the intersection of 2 lines, I just take the cross product again. So the points and lines, as I said, they form a dual in projective space, and that means really given any formula, I can sort of switch back and forth between what are the points and what are the lines. So when I told you that L transpose P equals 0, and I said L was the line and P was the point, well, that's just because L is for line and P is point. If this was some other language where L stood for point and P stood for line, you'd all be really confused. But basically what it would mean is that I was thinking of one is the line and the other is the point. We're going to make use of this not in the next lesson, but in the one later when we talk about fundamental matrices, where, just to give you forward-looking a little, remember that if I have a point in a stereo image, it has to appear somewhere on a line in the other, that's the epipolar line, and vice versa, these pair of epipolar lines. So projective geometry will make it real easy to go between points and lines. So just reviewing, in homogeneous coordinates, given 2 points, P1 and P2, if I ask you to find the line, no problem, just take their cross product. L is P1, P2. No algebra required. Well, other than doing a cross product, no thinking about lines equations or something that Mrs. Murphy taught you in 8th grade about how to go from, nope, you just take the cross product. Likewise, if I have 2 lines, A1x, B1y, equals 0, a2x plus b2y plus c2 equals 0, and I want to know the intersection of those two lines. That actually took a little bit of work in Mrs. Murphy's class, right? If I gave you the equation of two lines and I told you to find their intersection, you had to think about, well, I have to sort of make them equal and solve these two simultaneously. No, you just cross them. You know why Mrs. Murphy didn't teach you that? She didn't know. It's a long story about algebra teachers. Anyway, cool. Here's a quiz. How can I tell whether a point P is on a line L in the image? Okay, so I give you a line and I give you a point. How can I tell? Well, that's easy. I can just, A, take the cross product and see if that's 0. Okay. B, no. You want to take the dot product and see if that's 0. C, check, they're both 3 vectors, right? So I can add them and check them if the magnitude of the sum is greater than 1. Thinking about it this way, I have some point P in the middle there, right? That's projective ray is in that plane, and it's therefore perpendicular to the original line. So basically, you would just take the dot product between P and L, and if that's 0, then that point P is on the line. So the answer is B, I think. I think that's what I said before. Isn't that right? Isn't that right, Megan? B?
Yes.
Yes, she's right. She's paying attention. To finish our little tutorial on projective geometry, talk about something that's really more a vocabulary issue. There's this notion of ideal points and ideal lines. So ideal points come this way. We said that points are the intersection of a ray from the origin hitting the image plane. Okay, fine, no problem. And all the rays will hit that plane unless what? Unless the ray is parallel to the image plane. If the ray is parallel to the image plane, where does it intersect the image plane? We answered this before. We said you had to go, they intersect out at infinity. Remember, you had to go ask somebody high in the Himalayas about why that's true? That's the second time. The joke was so good the first time, I thought I'd use it a second time. Anyway, but the idea is that this notion of an ideal point is essentially a point at infinity. And the way you get a point at infinity is that you have z, the last term, it's x, y, 0. Scale being 0 gives you a point at infinity. And if you want to think about that, what happens when you divide by 0? X and y blow up and they go to infinity. So that's an ideal point. And the problem with an ideal point is that the ray that's supposed to define it is parallel to the image plane. Well, what about a line where the normal that defines the plane is parallel to the image plane? And that's shown here. It's a little difficult to see, but here's our normal right here. And you'll notice it has a z value of 0. Okay, so it's parallel to the image plane. Well, that's actually okay. What it means is that the plane that it defines is also going to be perpendicular to the image plane, which means it's going to go right through the origin. So the ideal line corresponds to an image that go through the origin, or the principal point. And that's typically in the middle of our images, but remember, your images might be offset. So an ideal point is off at infinity. An ideal line goes through the origin. We've been doing mostly our projective geometry here thinking about images. So we're talking about 2D projective geometry, so our homogeneous coordinates are 3 long. Well, you can naturally extend this to 3D as well. You remember the equation of a plane, ax plus by plus cz plus d equals 0. So the homogeneous coordinate is now just a 4 vector, wx, wy, wz, w. But of course, we've already seen that, right? When we first introduced extrinsic coordinates and we talked about combining rotation and translation, we introduced this notion of the 4 vector. And so in the 2-dimensional case, we had a duality between points and lines because they were both represented by 4-dimensional vectors. In 3D, we have a duality between a plane whose normal is ABCD, okay, that's the dot product, is represented by a 4 vector, and a point. So instead of points and lines like it is in 2D, it's points and planes in 3D. And the projective transforms, instead of 3x3s, are just 4x4s. So I wrote here that P prime equals TP. Okay. Well, that's just the 4x4 transformations that we had seen before. So since we've already seen that, we're not going to talk much more about it. Going forward, like I said, when we talk about fundamental matrix, we'll talk about projective geometry in the 2D case using the 3 vectors. All right, that ends today's relatively short lesson. We just a flavor of projective geometry. There are entire, as I say, books. There are entire lifetimes dedicated to projective geometry, mostly in France. They've got this thing about it. But in particular, out of France came, from Olivier Faugereau's group and others, was the application of projective geometry to computer vision. And it really revolutionized some of the work that was gone in terms of how people thought about stereo and other types of relationship between views. What we're going to do is we're going to use this a little bit in our next 2 lectures where we talk about what's called the essential matrix and the fundamental matrix. Those are a little more intense, so hang on. Welcome back to Introduction to Computer Vision. I'm Aaron Bobick still, by the way. Normally when I'd introduce something, I'd say who I am, but I guess you know. Okay. So last time we talked about projective geometry and sort of this relationship between lines, points, and planes and using sort of the projective relation and homogeneous coordinates as an easy way to describe these things. Today we'll use this a little bit to talk about the relation between 2 calibrated cameras. Next time will be uncalibrated. Just to contextualize it again a little bit, we have these projective transforms that are these matrices. These are 3D matrices, 3x3 matrices that operate in 2 dimensions that can transform an image in a variety of ways. For 3D, we talked about it being 4x4. We also talked about transformation they're called homographies that would map between planes. This is going to become very important, not in this lesson, but the next one, because we're going to be talking about recovering homographies that map between image planes. We also introduced projective lines, and we talked about that a line in an image plane was just the intersection of the image plane and a plane through the center of projection. That plane would be defined by a normal L, and that's why both a line and a point are 3 vectors in this homogeneous or projective space. And we showed some really cool things. We showed how the equation of a line is represented by the normal components in this projective space. And then a little bit of some cool operations that if I gave you 2 points defined in terms of projective coordinates, you could find the line that connected them by doing the cross product. Likewise, if I gave you 2 lines, you could find the point of intersection by doing their cross product. And these are some tools that we're going to make use of going forward. So let me motivate the problem. Remember stereo? Twice? Good. All right. So if you have 2 views of the scene, and these are 2 cameras that are not necessarily going to have parallel image planes, just 2 views, what is the relationship between the location of a scene point in one camera and its location in the other camera? That was what we wanted to know. We wanted to know if we could know something about that relationship so that we went looking for the matches, we could use it as a constraint. Just to animate it a little bit, if we have a pair of points. So the idea is we have a point P out there in the scene. That point images to some location in the left image plane, center projection 1 here, and that line maps to a line in the center projection number 2, and that was what was referred to as an epipolar line with respect to that point. So if you're looking for that point, it's going to have to be somehow on that line. Likewise, the ray from the other center of projection maps to the corresponding epipolar line in the other image, its center of projection. And those pair of epipolar lines, we showed before that they're defined by a plane called the epipolar plane. And that plane is defined, well, the simplest way of thinking about it is that it's defined by this baseline vector, so the translational vector between the 2 centers of projection and this world point. Or you can think of it as being defined by the 3 points, P, CP2, CP1, that's the epipolar plane. So we have a different epipolar plane for each point out in the world. We then talked about what we call the epipolar constraint, right? The idea was if I know about my epipolar lines or I know about the epipolar planes, the epipolar constraint means that if I have a point P in the image on the left-hand side, there's only a one-dimensional search in the right-hand image to look along. That was the epipolar line. For the parallel image planes, everything lined up, it was the same horizontal line. But in general, if I have verged cameras, we showed your epipolar lines weren't going to be parallel. And here was this example where we had converged cameras and corresponding epipolar lines. It also allowed us to define a couple of terms. So the baseline was just the vector separating the 2 centers of projection. The epipolar plane we just talked about, given a world point, and that baseline defines the plane. The epipolar lines were the intersection of the epipolar plane and each of the image planes. So that's a pair of corresponding epipolar lines. The epipole of each image was the point in the image plane that intersected the baseline. And we said sometimes you don't actually see that. In fact, if we go back to this pair of images here, all of these would have intersected over here. So if this image had been huge, you would have been able to see the epipole, but because it's in some sense cropped out, you can't always see the epipole. The problem with everything that I just showed you is it would be very difficult to turn it into code. Why do I mean that? What I mean is I've been showing you everything in terms of geometry, right? I'm like waving my hands and we got points, etc., whatever. Computers don't do so well with waving hands, and despite what my undergraduates say, okay? What we need to do is we need to go from the geometry to algebra. Because believe it or not, computers are fine for algebra as long as you know what you're doing. That is, you can convert algebraic expressions into computations. In fact, we talked about that earlier. But it's very hard to go from geometry to computation. And the way we're going to do that is we're going to take the geometry and then convert that to algebra. So we're going to start off today with a pair of calibrated cameras. Okay, so here's my pair of calibrated cameras. I have two camera centers, OC and OC prime, and they're both looking at some world point X. And it's viewed in the two images, and it's seen here. Because these are calibrated cameras, I'm going to assume that I know the translation t along the baseline. The t is the vector that is the baseline, right? So if I have to shift, 2, 7, 9 to get from one camera to the other in x, y, z, that's what my translation would be. And I also know r. I know the rotation matrix that you would have to rotate one camera center to become aligned with the other camera center. That's what it means to be calibrated. So we write this way. Okay, it says from geometry to algebra. We're not quite there, but we're almost there. But basically what we're saying is the location of the point x in the prime frame can be expressed by rotating x as appearing in the non-prime frame and then translating it by t. Right? That's just the equations we had before. I know this is not the homogeneous version. That's okay. In a minute we'll make everything beautiful. Before we make everything beautiful, a couple of reminders. Actually, this is the first reminder. Or an aside, I should say. And it's about cross product. The second one's about cross product too. So the first one is to remember that a cross product, so A cross B, gives you a new vector C. And that vector C has the property of being perpendicular to both A and B. So it's in the direction that's perpendicular. And you may also remember that the magnitude of that vector is equal to the sine of the angles between them, which should make you realize right away that if I take any vector A cross itself, that's going to be 0, because the angle between its vector and itself is 0, the sign is 0. So A cross A is 0 no matter what A is. Okay? So A cross B gives you C, C being perpendicular to A and B, and A cross A is equal to 0 no matter what. So here we start our little mathematical foray down into making it from geometry to algebra. So I just wrote what we had before. X prime, the position or location of x in the prime frame, can just be expressed as having rotated the x frame by the r amount and then translating it by t. All right? Great. Let's just cross both sides of that equation by t. So we have t cross x prime on the left, but on the right we have t cross, and it's just because of distributed property, it's t cross rx plus t cross t. All right? And by the way, I wrote here that this is normal to the plane. Remember that t cross x prime is going to be something that's perpendicular to both of them, so that would be perpendicular to the epipolar plane that we're showing here. We'll maybe make use of that in a minute, but I just want you to realize that. More importantly, what you should see is that we've got t cross t here. What's t cross t? Not very much, otherwise known as 0. Okay? So that just means that t cross x prime is equal to t cross rx. Got it? Okay. Now, let's take both sides of that equation, and I'm going to dot it with x prime. So we got x prime dot t cross x prime equals x prime dot t cross rx. I sure hope you're reading this, because listening to me sounds ridiculous. Okay? Well, let's take a look at this left-hand side. Okay? T cross x prime gives us what? Well, it gives us a vector that's perpendicular to the plane containing t and x prime. So it's perpendicular to t and it's perpendicular to x prime. And then I dotted it with x prime. So what am I going to get? 0, right? Because it's perpendicular. And if everything goes well, there it is in yellow. 0 is equal to x prime dot t cross rx. Okay? So far, so good? Good. Time for aside number 2. This one's kind of cool, actually. It's more about cross products. So you might remember there's a simple formula for how you can get cross product. You basically do ijk, and then you do a1, b1, c1. You do your first vector, your second vector, and then you do essentially the determinant, and that gave you the vector. Remember that? Remember that? Remember that? Okay, maybe you don't remember that. That was the formula for cross product. If you had been really smart, you would say, you know, I can just write this as a matrix multiplication. Okay? So I just build this little matrix here from my A, okay? And I take my vector B here. And so that says that the first component of C is going to be what? Well, it's going to be minus A3 B2 plus A2 B3. And that is the first component of the cross product of A and B. Same thing for the second component and third component. So we can just write cross product as matrix multiplication. So I'm going to define a little operator, and this little operator is written here. This x, that means cross product, okay? So when I do this little bracket ax cross, that means that I'm going to substitute in this matrix, which is sort of the cross-producting matrix of A. So if I wanted to do A cross B, I would just multiply this matrix times B. So the notation, as I wrote here, is A cross B equals, and just this bracket, and here the font's fixed, it's just this bracket AX times B. Something that we're going to make use of, not this lecture, but next lecture, is, and I'll leave, I love it. I used to love it when professors said this. The proof is left to the reader, okay? But you could actually do this. Figure out what the rank of this matrix is. And if you come out with any number other than 2, try again, because the rank of this matrix is 2. Okay, so it's a 3 by 3 matrix, but the rank of the matrix is 2. And we're going to make use of that later because, as you may remember, if you multiply matrices together, ranks can only get smaller. I multiply a rank 2 matrix by some other matrix, I've got a rank 2 situation. Back to where we were. Remember this equation? 0 is equal to x prime dot t cross rx. We just rewrote that again. So now I can get rid of that whole cross product thing, right? And put that cool little funky cross product notation in there, right? Right. All right? So let me do a substitution. I'm going to let E be just this T cross R. Okay, so it's just this substitution in here. Well, as soon as you do that, you realize I have this really beautiful, elegant expression that says x prime transpose E x equals 0. And E is what's called the essential matrix. And what's cool about the essential matrix is that it relates the point x and the same point, but described in the other camera frame. And note that these are world points in these frames for these calibrated systems. In a little bit, we'll talk about the relation between world points and the image points, and it's a little bit closer than you might think because of the projective geometry. In fact, one way of thinking about this real easily is this is equal to 0, right? So what if I multiplied x by some value a? Would the equation still be true? Of course it would. So not only is it true for the point out here, as expressed in this coordinate frame, it's true for every point along that ray expressed in that coordinate frame. Likewise for every point along that ray expressed in that coordinate frame. Ooh, that means it also talks about image points, but we'll get there. All right? One last thing, and this is you're not going to totally get that this time, but that's okay, you're going to get it next time, all right? We said that this works for sort of any point along that ray, and so you can think of that as the homogeneous representation of all the points along that ray. So our E is our 3 by 3 here, times this 3 by 1, so this is another vector here, all right? We'll just call that L, okay? Why am I calling it L? What does L stand for? Well, in some weird language, it said it stood for point, but in our language, it stands for line. So remember that X transpose L, or P transpose L, or L transpose P, was the definition of a line in projective geometry. So what this means is if I knew where some point was in the image, so I know what ray it's along in the image, so I know where it is in the image, I could put that point into this equation and I would have this L, which defines for me a line in the other frame. Just x prime transpose L equals 0. That was the definition of a line in our projective geometry. So in other words, if I gave you a point in one image of a calibrated set of cameras, there's a line in the other image that that point must lie on. What's that line called? That's the epipolar line. But notice that everything on this side of the slide is algebra, right? Forget all the geometry stuff. So what we've done is we've now converted the epipolar constraint into an algebraic expression. Thank you very much. No, that's what we're going to use. Okay, great. All right, so you ready? This is actually a good quiz. You know why? Because the quiz is going to make us do some work. So that was fine, what I just showed you for some converged cameras. What about if the image planes are parallel? What happens? A, well, that's a degenerate case, and we're going to see that in just a minute. B, that's fine, it's no problem. It just means that R is the identity matrix, and the math just works. C, I have no idea. Okay, that's usually a bad answer to put on a final just saying. By the way, and so C is not the answer. I have some idea. So the answer to the rotation matrix is just the identity. So let's work through this a little bit. Let's do the essential matrix computation for the example of parallel cameras. Okay? So first, what is, so by the way, you recognize this picture? Right? This is the picture of our parallel image planes when we were doing the stereo, the derivation of the relationship between disparity and depth. So I have two parallel image planes. Nothing is rotated. Oh, nothing is rotated, so what's the rotation matrix? Well, it's just the identity. Great. All right, what's T? Well, what was T? T was the translation between the two camera centers. Well, in the geometry that we've defined here, the camera center has just been translated at amount B in the x direction or negative B in the other x direction. Doesn't matter, but we'll just say it's minus B, 0, 0. Okay? So T is just minus B. All right? Well, that means I can now compute my essential matrix, because my essential matrix, defined before, was this weird cross product thing of T times R. R is the identity, so we just plug T into the cross product little formula I gave you, and it looks like that. So that's our essential matrix. Let's make use of that matrix. All right? What does the essential matrix constraint say? The essential matrix constraint says that P prime times E times P equals 0, right? Where P prime and P are the location of the points, one in the prime frame and one in the regular frame. All right? So where are our points P? Well, it's in some location cap X, cap Y, cap Z, okay? Which is also, in the other frame, cap X prime, cap Y prime, also Z, because the Z's are the same because our planes are parallel, right? Right. So here are our points written. And the first time I wrote them as we said before. P is X, Y, Z. P prime is X prime, Y prime, and the same Z. But kind of written kind of cool over here, right? We assume that under normal projection, little x is F times big X over big Z. So I'm just writing big X as Z times little x divided by F, okay? And that's how I entered in these things here. Same thing with the primes over there, okay? Let's put those points in our essential matrix equation, all right? So I just inserted them here using our E, and now I've done something a little bit sneaky again. So here I have P prime, E, P. But you'll notice I've now divided my points all the way through by the amount Z over F, a constant, right? Z is whatever, I don't know what the value is, but it's some constant value. And F, I might not know what that is, or I might, some value. And I just divided all the points through by that. Now, why am I allowed to do that? See, in class, everybody yell out the answer. But over the ether, you guys can say, because it equals 0, dummy. All right, so I can multiply anything I want by a constant and it stays equal to 0. And I just wrote it this way to make it easier to see the equations that are about to happen. So I just divided by z over f. Copy that equation over again. Multiply out the first one. So now we have x prime y prime f dotted with or transpose of 0 bf minus by equals 0. Multiply it more again. We get bfy prime equals bfy. B is a constant, f is a constant, divide through, and it just says y equals y prime. Y equals y prime. What does that mean? Oh, that means if I have some point in the image at location xy in the regular frame, the line y prime equals y is the line that this point has to be on. And think about what this is. So a point's at xy, so it's at some x location and it's y. Let's suppose y is 17. The equation y prime equals 17 is what? That's a horizontal line at height 17. So what this says is our epipolar constraint for parallel cameras, right, is that given a point in the image, the corresponding point is on the same horizontal line. Except last time, I just had to make you believe me. In fact, you didn't even ask the question because it's very quiet in here. But it made common sense that if these cameras were lined up, it should be at the same line. Well, common sense doesn't get you very far in mathematics. Here is the derivation, if you will, that from parallel planes you can lined up this way that your epipolar lines are horizontal. Okay? So the answer to that previous quiz of does this work for parallel planes, it works beautifully actually. The rotation matrix is just the identity, and it derives out that your epipolar lines are, in this case, the parallel horizontal lines at the same height. Cool, huh? Okay, so that's called the essential matrix, and it's maps between calibrated systems. And what was really important about this whole operation is that we converted the geometric constraint that we had talked about back in the stereo days when we were talking about epipolar planes and looking for them. We converted a geometric constraint into an algebraic constraint. All right. But you ask, suppose I have uncalibrated cameras. Geometrically, thinking about it, if you gave me enough points that you told me this point corresponded to that and this point corresponded to that, it feels like I should be able to figure out how the epipolar lines are constrained. So what I need to do is to somehow figure out the algebraic relation between images given those correspondences, and that algebraic relation will give us a relation between a point in one image and its epipolar line in the other image if you gave me enough correspondences. That's what's called the fundamental matrix, and that's what we'll do in the next lesson. Welcome back to Introduction to Computer Vision. Today we're going to wrap up our unit on essentially calibration in stereo. We're going to talk about the fundamental matrix. Last time we developed the relationship between two views of two calibrated cameras where I actually knew the rotation and translation between them. And what was cool is we essentially went from what the geometric constraint was, that whole epipolar constraint that we had shown very early on, and we derived from the geometric constraint an algebraic constraint. And in particular, we defined something called the essential matrix, which related between two views, or I should say world points of two calibrated cameras. So the same point in the scene, the two different views of it, what the relationship was between them. But you might ask, suppose I don't have a calibrated camera. All right, well look, let's think about the intuition. If you gave me two images, and you gave me enough points to tell me that this point is this one, this one, this one, this one, gave me enough corresponding pairs, it feels like you should be able to figure out, say, the epipolar lines, that is how the lines map across, and what the correspondence should be for all the other points. And when I say correspondence, where they can be along the epipolar line depending upon their depth. Well, today what we're going to do is we're going to make that intuition real. We'll do the mathematics of this relationship between two uncalibrated points. Let's talk about, I'm going to call it weak calibration. And what I mean by that is we're just assuming that we've got two projective cameras so that they're going to behave like projected cameras, but in particular we don't know anything about focal length or their offsets. But we are going to assume, for example, that we don't have radial distortion. We're going to assume that we don't have a non-uniform stretch of the image. So, but when it's, say, weakly calibrated, that's all we mean. We correct for that. So the main idea is that we're going to estimate the epipolar geometry from a set of corresponding points between uncalibrated camera images. And we'll probably use a large set, so it's going to be somewhat redundant in order to make this thing more robust with respect to noise. All right, so let's get started. So before, from our all our projection stuff, you'll remember that we had this projection that went from a world coordinate through our extrinsics to our intrinsics to a projective representation of the image coordinate, right? And so to get the non-homogeneous, you had to divide through. So it's written here like it's a scale, W times the image point is equal to the world point times our extrinsics times our intrinsics. So phi is just as we did before. We're going to use a 3x4 version here since K will be a 3x3, where the left-hand side is that rotation matrix and the right-hand side is the transformed translation. And you'll notice a slightly weird form written here of it's R times T. And all that's saying is that if you know the translation in one frame, you might have to translate, you might have to express it in the other frame depending exactly on how you're doing this. Don't worry about that detail. Okay? So that's phi, our extrinsic parameter matrix. And K, if you remember, that's our intrinsic calibration matrix. And the K that I'm showing you here has a focal length and an X scale and a Y scale. And of course, as we said before, they're multiplied together. You really only need two numbers. You've got F divided by SX and F divided by SY, so they always appear as multiples like that. But we have a scale in both directions. We have the offsets. But what we don't have is we don't have any skew. That is that this value here is 0. That makes this math a little bit easier, and as I said before, in general, for modern cameras, skew just isn't an issue. All right, so I'm going to write that this way. The point in the image, and this is a homogeneous point, is a point in the world times our multiplied by the extrinsic matrix multiplied by the intrinsic matrix. But this, of course, is just the world point put through the extrinsics. That is the location of the point. It's a 3D point, but it's in the camera frame. Remember that the extrinsic matrix maps us from some arbitrary world frame into the 3D frame of the camera. Okay, so that we're going to call that PC. And so we can write down this very simple relationship that K, the intrinsics here, maps us from the point in the camera coordinate system to the homogeneous point in the image. Okay, so P in the image is equal to K intrinsics times P in the world. It's the point in the world, but expressed in the camera frame. Now, this is as if I had phi and I had K, etc., but I said that this was uncalibrated, right? Right. So let's suppose we have a given camera, Pm equals K times PC. All right? Now, see that K? That K intrinsics, that's a nice, assuming we don't have zeros sprinkled through here on the diagonal, that's a nice invertible matrix. So I can invert that K, and that's what's shown here. Okay? And what this says is that I can go from the image back to the point out in the camera frame. Now this should bother you a little bit, just a little bit, because it says this equation's fine, okay? We derived this a long time ago. We said if you gave me the 3D point in the camera's frame, I knew where it landed in the image. But this second equation is saying that I can go backwards. You can tell me where I am in the image, and I'll be able to tell you where I am in the world. And that seems wrong because that whole projection operator, and then you say, aha, this is not a regular 3D point, this is a homogeneous point. And you remember the projective geometry stuff we did a couple times ago? That's anywhere along the ray. And that's correct, right? If you tell me where I am in the image, if you just tell me the basic camera intrinsic geometry, I now know the ray in space that point came from. And that's all the projective geometry, the homogeneous coordinate is telling me, that if you give me the point in the image and the intrinsics, I can tell you the ray in space, which is the same as a homogeneous the homogeneous coordinate in the image. Okay? That's why we can go from an image to what feels like a world point, but is really just the ray. So now I can take that equation, and I can say, well, suppose I've got two cameras, typically called the left one and the right one, or the up one and the down one, or the forward one and the back, or just the main and the prime. Two cameras, okay? Here written left and right to be convenient, okay? Now, we have a different internal calibration matrix per camera, right? The two cameras may be the same kind of lens, same everything, or they may be quite different. All I need to think about is that there exists an intrinsic calibration matrix for each one. And by the way, this is uncalibrated, right? Right. So I don't know what it is. I'm just assuming there is one and that it looks like that one that I showed you before. I don't know what the values of those parameters are. Okay? All right. Now comes the magic. All right? Just repeated both equations here. This says the location of that point in the right frame in terms of the ray. This says in terms of the left in terms of the ray. Okay? But we know something about the relationship between a point in the right image and a point in the left if this were calibrated, right? What did I know there? Well, that was last time. I know there's this thing called the essential matrix that would relate the ray to the point from the right frame to the ray to the point in the left frame. And the relation between them is called the essential matrix. Now, I don't know what the essential matrix is. Why? Because I'm uncalibrated, but I know there would exist one. Okay? So if I assume for a moment there exists one, then I can rewrite this equation like that. Okay? So all I did was substitute for the point ray in the right frame, which was from here, and I pulled that down into here. Okay? And do the same thing on the left. Copying that over, well, this is just matrix multiplication. I hope you all know that A, B, bracket transpose is just B transpose A transpose. If not, trust me. All right? So I can regroup using the associative property here such that here I have the transpose, and that's where this comes from that. Okay? And then what I can do is I can combine this whole thing, the K inverse, the intrinsics from the right, transpose, times E times K inverse of the intrinsics on the left. Remember, I don't know what they are, but I just know they exist. And I'm going to call that whole thing F. And when I do that, I end up with this beautiful, beautiful, beautiful equation. It just says that P transpose of the image point on the right, okay, so this is from the image now, times F times P in the image on the left equals 0. Okay? And this is a relationship between image points, which I can just write this way as P transpose F P prime equals 0. P being in one frame, P prime being in the other frame. That is the fundamental matrix constraint. That's what's going to allow us to solve for the relationship between one view and another. Given enough points that correspond, enough P and P primes that correspond, we're going to be able to solve for F. And once we do that, we know what relates the two images. Or this can just be written as P transpose F P prime equals 0. P in one frame, P prime in the other frame. It's the relationship between the points. Now, with this equation, I'm going to be able to do a lot of things. In a minute, I'm going to show you how we can solve for F. That is, if you give me enough points P and P prime that correspond, I'll be able to solve for F. But the other thing is, F is actually very powerful in terms of describing how the epipolar geometry works. All right, if you had actually been here while we were recording this, you would have seen that I just walked around the room 17 times trying to get my act together because I started to talk about this and my tongue just was but here goes, okay? Couple things, all right? So this relationship here, that's the relationship that happens algebraically between corresponding points. P and P prime are the image points of the same point outside in the world. Now, we remember from our epipolar geometry, so like that's over here, that if I've got some point, let's say it's right here in the image, I know that that's on this ray somewhere, and therefore that point must be on that epipolar line. That was the geometric constraint that we had derived earlier. So the P transpose F P prime equals 0 is the algebraic one. The drawings with the epipolar lines was the geometric one. But clearly they relate. So you'll remember from our projective geometry little tutorial that we said that the equation of a line, right, could be written a couple of ways. I'm going to write it this way. P transpose L equals 0, right? Remember, L was that normal to the plane, and all the points P had to be on that, in that plane and would be perpendicular to it. So notice, here we have P transpose, here we have this P transpose, here we have this L, here we have that L, here we have that FP prime, okay? These equal 0 is a line. That's the constraint that has to equal 0. What this means, and that's what's written here, is that this L, which is FP prime, is actually the epipolar line in the P image. Okay, so remember, I'm going to erase these, right? It's going to be multiplying a point in the P image. So L equals FP prime is the epipolar line in the P image associated with the point P prime. Also, just reversing this, that means that F transpose P is the epipolar line in the prime image, the P prime image, associated with the point P. All right? So what the fundamental matrix does is it gives us the epipolar line constraint between two views. So if I know what F is, I can compute the epipolar lines. In fact, you can just, for a given point, I just take F transpose P, and that's the epipolar line in the other image. And that makes sense because the F is what we said takes all of the, goes through the intrinsics of one, through the extrinsics, the intrinsics of another. And so the only thing I don't know for some point that I'm seeing in my left image is, well, since I don't know its depth along that ray, it has to be along this line. That was the geometry. So the fundamental matrix equation reduces that geometric constraint to an algebraic one. The great thing about video is you can go back and take a look at this. We'll also, in the class notes, there'll be some pointers to some texts where you can look at it and learn it from people who are way more articulate than I am. But that's the relationship between the fundamental matrix and the epipolar lines. Go back and look again. Do it again. Okay, so now you're here, and now you really got it. You understand it all, so you should really teach this class, but I'm stuck here on this side of the screen. You're stuck there, so I'll keep going. Okay, great. All right, now comes something cool. Again, a little bit complicated. We know that P prime is on the epipolar line corresponding to P in the other image. Okay, that's what this equation says, if this equation holds. But suppose P prime was on the epipolar line in the prime image for every point P in the original image. You might say, well, how could that be?
How could that be?
Thank you, Megan. Well, the way that could be is, suppose FP prime equals 0. Well, in order for a point to be on every epipolar line, well, there is only one point that's on every epipolar line. That's the epipole. So the way you find the epipole given the fundamental matrix is you solve this equation. And remember, there's two epipoles. There's the epipole in the original frame and the epipole in the prime frame. And so you just solve each of those equations, Fp prime equals 0 or F transpose P equals 0, and that identifies for you the epipoles in the image. So this F matrix is very powerful. It tells you everything you need to know, or almost everything you need to know, about the way the points relate to one another in terms of their projective geometry, and that lets you do things like find the epipolar lines and the epipoles. Pretty cool. One last thing about the fundamental matrix, and we'll look more at this later. The fundamental matrix is actually a 3 by 3, right? Because this is the homogeneous coordinate of an image point, so it's a 3 vector, okay? But I will tell you, we're going to show this in a little bit, that the F matrix is actually singular. And the reason for that is if it wasn't singular, it would map between points and points. But in fact, it maps between points and lines. So it maps from a 2D point to a 1D line. And that's what sort of requires that it be singular. We'll do a simple algebraic proof of it later. But it makes sense because when you give me a fundamental matrix and I give you a point, you can't tell me the point over here. All you can tell me is the line. So we go from something that has 0 degrees of freedom, a single point, to something that has another degree of freedom, and that's because the rank of the fundamental matrix is only 2 and not 3. Like I said, we'll show that to you in just a minute. So now that we have the fundamental matrix, well, so what? Well, as we said, it relates between the pixel coordinates in the two views. And it's much more general than the essential matrix because we've removed the need to know the intrinsic parameters. If you told me the intrinsics, okay, then I could figure out the rays that correspond, and if I know the rays that correspond in the 3D camera coordinates, I could compute the essential matrix. I could figure out the real rotation or translation. But if I have two arbitrary cameras that aren't even necessarily the same, the fundamental matrix allows me to relate them without worrying about the intrinsics or the extrinsics. So the bottom line is, if we estimate the fundamental matrix from the correspondences, then we can reconstruct our epipolar geometry without having to worry at all about the intrinsics or extrinsics of the camera. And that's what's done here. Here you see two pictures. I think this is also courtesy of stealing from Andrew Zisserman. And you have some pixels on the left and some pixels on the right, and then they were put into correspondence. The idea is I gave you corresponding points, and now the lines that are drawn on here, those are the corresponding epipolar lines. So in fact, if you take a look real quick, so you'll notice that, you know, here's a point right on the bottom edge of that window, and this line lands right on the bottom edge of that window. So these are corresponding epipolar lines. Any point that's along this line is also going to be along that line. Let's see, does that really work? Let's see, it goes across this chimney thing. Yep, there it is, right there. Okay, so that's finding the epipolar lines by given the correspondences through solving for the fundamental matrix. So let's work a simple example, all right, of finding the fundamental matrix. And a bunch of them out there. One that I'm going to show here is one that's a little bit different because it's not as sort of trivial. Here's the one of the two side-by-side stereo views. We'll do it a little different. And remember, a fundamental matrix gives a correspondence between any two views. It doesn't matter where the cameras are taken, okay? So for example, my images could look like this. And you might say, whoa. Okay, you might not say whoa, because that would be only if you were born in the late 60s or maybe early 60s. But here I have a picture, and the white lines drawn on it are meant to be sort of nominal epipolar lines. I took a picture, and then the camera moves forward, and I take another picture. Can I do a fundamental matrix for that? Of course I can. In fact, that's what this geometry is meaning to show here. It's a little hard to see, all right? What I have here is that I took one picture, and my camera center was there, and then I take another picture, and my camera center is moved forward, and if you connect those and slice the image, those are the epipoles. So all the epipolar lines have to go through the epipole, and that's what this is showing you, right? The epipole is right in the middle of my picture. Here's not exactly in the middle. It's off to the top. It's actually to the side a little bit. I'll show you in a minute. But all the epipolar lines have to go through the epipole. And that's another way of saying is, you just think about that intuitively. If I move straight ahead and I'm looking straight, the points move along that diagonal out from the center. So that means that if you give me one point in the first image, it's going to be somewhere along that line in the second image. And how far it's along that line will be a function of its depth. Okay, because remember the amount that points move between one image and the next, function of depth, going way back. Remember disparity. The closer something is, the more it'll be disparate. Something that's very far away, like the moon, doesn't change much at all. Okay, so they're going to move along these epipolar lines. So we're going to use this as an example because it'll be very clear whether you got the epipolar lines right or you got the epipolar lines wrong. So how do we compute the fundamental matrix from the corresponding points? All right, so here I wrote the fundamental matrix equation, and you'll notice that each point gives us one equation, and that's written here like this. So u prime v prime 1, that's the projective similarity of the point in the prime, times the fundamental matrix, times uv1, that's the other point in the original image, equals 0. Okay? That's a single equation per point. All right? So copy it here, and I can just multiply this whole thing out, and I still have my one equation per point. And on the left-hand side, these are my knowns, right? So I take the u primes and the u's, or the v primes, or the v prime and the u, or just its individual, etc. And here are my unknowns, right? The unknowns are the elements of the F matrix, okay? So 1 point, 1 equation. Well, I just collect n of these, right? N is however many number of points that I have, and then I'm going to solve the thing. So how do we do that? Well, there was originally something called the 8-point algorithm. It was done by, I think that was done by Christopher Loggett Higgins, and for a while it got sort of a bad rep because people thought it was very unstable, and that's why I put down that it was the infamous 8-point algorithm. Now, you might say, well, why can I do with just 8 equations? I've got 9 unknowns. Well, remember, p f p prime equals 0. I can scale the f any way I want, which means, for example, I could set that last value to a 1. Not a very good way of doing things, but it does mean that if you gave me just 8 points, I'd have 8 equations, and because I set the last one to 1, I would have 8 unknowns, and I'd be able to solve it. If I have more than 8 equations, right? So then I've got this, let's suppose I've got n. So I've got n equations with 9 values that are homogeneous. Have we seen that before? Yes. Remember when we solved very early on, when we were trying to solve for the total calibration matrix between the world and the image, and we had the M matrix, and we said, well, there's 12 elements in here, but there's not really 12, right? There was really only 11, but if we used a whole bunch of points, we talked about you could set one element M to 1, but that wasn't such a good way. What was a good way? The SVD, remember you've got this A times M equals 0, or in this case, A times F equals 0. You take A transpose A, take the singular value decomposition, or you just find the eigenvectors, and you pulled out the eigenvector with the smallest eigenvalue. We've actually seen this now 3 times. I did it explicitly for you in the very first example, so you can go take a look at that. But that's how you solve it. And by the way, you would typically use more points than just 8 or 9, or you use however many points you have. So you solve this. And what happens? Well, your point matches aren't exact, are they? No. So you solve this, get an F. With an F, I can draw some epipolar lines, right? And if I used, and these numbers were meant to represent coming from that picture, I would see this, okay? And that's technically called a mess, all right? Because you'll notice that the epipolar lines, they're not all intersecting at that single point, are they? No. Why not? Well, I'll tell you. So here I have the same system I had before, 2 camera centers, some point out there. And these are my 2 image planes, okay? Now, go in your Wayback Machine, well, not so far back, just a few lectures back. How do you map from one plane to another plane? Well, I told you before that if you have 4 points on one plane and 4 points on another plane, and you knew their mapping, you would then have the total mapping between the 2 planes, and that was called what? That was called a homography. Right? It took 4 points to get a homography from one side, from one plane to the next. All right? So we're going to pretend for a moment that we know the homography, we'll just call it H, that goes from the plane P to the plane that has P prime in it. Okay? So we're going to pretend that we know that. All right? And the other thing we're going to do is we're going to say, for some point P here, L prime is going to be the epipolar line in the prime frame that goes through this epipole E prime. Okay? So that's the 2 things I've set up. I'm going to pretend that I know my homography, and I'm going to also say that that's the epipolar line. All right? Now we do a little math. Okay, so L is that epipolar line. So how do I find this line? Well, remember, this is a line that goes between 2 points. If you remember, in projective geometry, if I have 2 points and I want to find the line that goes through them, what do? I just take the cross product. That was one of the cool things about the projective geometry. You gave me 2 points. take the cross product, you get the line. Give me two lines, take the cross product, you get the point that's the intersection between them. So here I just wrote that L prime is just going to be the cross product of E prime and P prime. But wait, we said that there's a homography H, okay, that maps between P prime and P. So I'm just going to substitute H times P for P prime. Okay, no problem. Then I'm going to use something else you learned, actually, just last time, all right? We said that a cross product can be written as this little matrix operator, right? Right. Okay, great. So that says, just erase that L prime is just equal to this cross product operator on E prime times H, the homography, times P, right? Right. Ah, but now, I said L prime is the epipolar line in the prime frame for the point P. That's what this is, right? This is the epipolar line for this point P, all right? Well, we just learned that L prime is just FP, right? F is the fundamental matrix times P. We learned this like 5 slides ago. That was the one that we repeated like 17 times. Well, okay, L prime is equal to this nonsense over here on the left, and it's equal to FP on the right. That means that this nonsense on the left, E prime cross product matrix times H, is equal to the F matrix. Well, remembering a little bit from your linear algebra, that means that the rank of this thing is going to be the rank of this thing, and this is rank 2. Told you this would come up before. Remember I said to you, and this was an exercise we left for the reader, that this little cross product matrix operator, where we took the A and we distributed amongst the 3 by 3, multiplied it by B for A cross B. And I said one of the things that we're going to need later, see I wasn't lying, is that the rank of that cross product operator is 2. So that means that the rank of F, which is just this matrix times H, is also 2. F is not full rank. But before, when I was solving for the elements of F, I didn't enforce that in any way. It's a 3 by 3. And whether if you use the SVD or whatever you do, it's not going to make it become a 2-rank matrix, even though it's a 3 by 3. So we have to fix our F to be a rank 2 matrix. So how do we do that? Fortunately, that's really pretty easy. It's pretty simple to fix that linear solution that we did before. So do what we said before, solve for F, and you can do SVD, where at that minimum eigenvector, or you can use the linear thing where you set it to a 1, although I don't like that method, okay? You solve for an F. Then what you do is you decompose your F using SVD again. This is another SVD, another singular value decomposition, and you're going to get out 3 terms, all right? Remember, SVD gives you U, D, V transpose. V is the lower dimensional orthogonal matrix of all unit vectors that are orthogonal to each other. U is also orthogonal, but of the full dimension. Now, what did D stand for? No, not Dalmatian, not dysfunctional, despite what you might think. D stood for diagonal. Okay, so it breaks down, it gives you a diagonal matrix. Now, if F is really a full rank 3 by 3 matrix, D is going to come out as a diagonal matrix with 3 non-zero elements. And D, normal SVD, is produced in a decreasing magnitude. Okay, so it goes from largest to smallest. So what we do is we take the D that comes out, and I just wrote that as RST here, okay? And T is smaller than S, which is smaller than R. And what we're going to do is we're going to create a new D, D hat, and just set that least value to 0, because it was supposed to be 0, because that would be a rank 2 F, would have a R, S, and 0, so we make it 0. Great. Once we've done that, we can build a new F, which I'll call F hat, using the same U that we got the first time, the same V that we got the first time, but we substitute in this new D, right? D hat, which is the one that is only got 2 diagonal elements. And that gives us a new fundamental matrix that has just rank 2. When I apply that to the example that I showed you before, you get epipolar lines that look like this. way, way better. In fact, you can see here the camera was not moving perfectly straight. It was moving off to the side just a little bit in that direction. And here is the epipole, right? All the epipolar lines go right through the epipole. So we've got the good F and all is happy in Oz. There are some cool things that you can do when you find the fundamental matrices that relate different views to each other, okay? Because essentially you can figure out which points correspond to which other points. One, which is really kind of interesting, is suppose I've got a pair of views of a scene, and what I'd like to do is do some stereo. And I know that if I solve for the fundamental matrix, I could, for every point, I could find the epipole that's along and search along that. But of course, every point lands on a different epipolar line. What you can do is what's called image rectification or stereo rectification, where you take your original image, and if you find the fundamental matrix, you can essentially unwarp, maybe that's not the right word, just rectify is the right word. So it's as if the two images were taken with parallel image planes that are aligned. And why is that good? Because it makes me happy. No, it's good because you can get public. No, it's good because then it means your stereo solution now is just moving along the horizontal line. So your search is not just 1D, because it was 1D before, but it's a particular known one-dimensional search. Namely, every point here corresponds somewhere along the corresponding scan line in the other image. And that was done nicely. Comes from this paper here shown in 1999, showing you a real example that they did that comes from their paper. Here you see two images taken from radically different views of this very weird sculpture. The lines that are drawn on there are the epipolar lines, and you'll notice they're skewed and they go off this way. All right. After you do the stereo rectification by finding the fundamental matrix, you get horizontal epipolar lines, which was the whole point and allows you to do the stereo algorithm. There's some more cool applications. There's a whole bunch of work in building up structures from multiple images taken of that same structure. And there's a system and a whole bunch of work that came out of the folks at Microsoft Research and also University of Washington. Here's an example published at SIGGRAPH. And they built a system called Photosynth. And what you can see here are a bunch of pictures that were taken of Notre Dame. And what these little things down here are meant to show are the locations of the image with respect to the structure. And that has to do with relating between the views that you have things. When you do that, you can do some really cool things. They basically launched this site, this whole phototourism, this idea of being able to put in your images, and this is their Photosynth. And I encourage you to check it out if when you're using this, we still use computers. In fact, here was a really cool demonstration done by Agarwal and back in 2009, isn't it? So what you're seeing is there's a whole bunch of these little dots. Those are camera viewpoints of the Colosseum in Rome. You should go see that. I mean, this is nice. See the real one. It's really cool. And this is just flying you around the reconstruction of all these points based upon the solution to where all these cameras were. And this all relates to first solving fundamental matrix issues and then getting the full 3D calibration. I don't want to claim that you can do this with just the fundamental matrix, because in fact you eventually end up getting full 3D reconstruction here. But the idea is you have to know how the points correspond. Summary slide. I love summary slides. For two views, and we learned at the beginning, there's a geometric relationship that defines the relation between rays in one view and rays in the other view. And we were referring to that about the epipolar geometry. These relations can be captured algebraically, besides geometrically. For the calibrated camera case, that was referred to as the essential matrix. For the uncalibrated camera case, it's the fundamental matrix. And the math that we've been going through has been talking about how you can find these matrices, how you can find these relations by just giving me the correspondences between points from one image to the next. All right. This ends the lesson on fundamental matrices. In fact, it ends the entire unit on calibration and stereo. I hope you realize that from these relationships, you can capture the geometry of the scene. That is, given some camera views, you can eventually figure out the three-dimensional locations of the points. So this is not image processing, right? This is actually vision where we recover a 3D structure. And if you're taking the OMS version of this of this class and you're doing the OMS problem sets, you're going to get to know and love these. Well, you're going to get to know, I hope you'll love these processes pretty well. That's it for this unit. Welcome back to Computer Vision. With this lesson, we're actually starting a new unit, which I've nominally titled Features in Matching. But really, the whole idea of this is to find reliably detectable and discriminable locations in different images. That is, I'd like to figure out a way that if I have some points in one image of a scene, I'd like to figure out which points are the same points in another image of the scene. Now, you might say, wait a minute, we just did that in stereo. But no, you didn't. You see, in stereo, the idea was that we were going to have these epipolar lines along which we would search. But remember, we talked about that in order to find those epipolar lines, we need to know the fundamental matrix. And in order to do that, we needed correspondences. So this is a way of finding correspondences. That's one way of thinking about it. Couple of resources. Forsyth and Ponce cover this nicely here in section 5, 3, and 4. And Salisky, which is that other textbook that we pointed you to, also does this well in chapter 4. We talked about that there were different ways of transforming images one to another. And, so I might have two images that are related by some transformation. And we talked about how if I know the transformation, I know it'll go from one image to the next. But suppose I have two images, and I'd like to figure out the transformation that takes image 1 to image 2. How would I go about doing that? Well, to do this, I need matching or corresponding points. So the way we're going to go about finding corresponding points is using something that we're going to call local features. And you'll notice it says a little 1 and a little 2 there. We're going to put some meat behind defining what we mean to be like local and what we mean to be features. By the way, some of you have taken machine learning courses and things like that, and you've seen feature vectors. That's not what we mean here. We're actually going to mean that later in the course. Here, features are going to be things that we compute about some little local spot. They're related to feature vectors, but we were here first. All right. Our goal is to find points in an image that can be found in other images. And by the way, not just found in other images, but found precisely. And what that means is, you tell me about it, I should be able to precisely determine where that point is. So just saying it's the middle of this gray panel, not so great. But if you told me it's this tip of this spear, that would be better in terms of being localized. Also, I want to reliably do the matching, right? So if I find this point, if I find a bunch of other points, I want to be really sure they say, nope, it's not this one, it's not that, it's definitely that one, right? So this is this idea of well-matched points, all right? So why do I want to do this? Well, we talked about things like I might want to recover the fundamental matrix to recover geometry. Remember we said that if you give enough correspondences. In robotics and other computer vision things, we might want to see how a bunch of points have moved from one frame to the next. And in order to do that, I have to figure out which points were which. Or I might want to build a panorama. Now, we've talked about this in general, but here's really a beautiful example. This comes from a paper by Brown and Lowe in ICCV in 2003. Let me just play that again because it's so cool. All right? And here what they've done is they've figured out with matching points how to place each one of the pictures on top of another. In order to do that, they had to find these matching points. Let's step through this just a little bit. So when we talk about building a panorama, what do we have to do? Well, we're going to have to sort of align our pictures in order to be able to paste them together. That's what we just saw. So to do that, here's the basic process. The first thing we do is we're going to detect some features, okay? And here features just mean some interesting points. In fact, we're going to define something called an interest point operator that'll find some points that we define to be interesting. Don't you wish you had an interesting person operator? You could just scan it around a room and it would just tell you who's interesting. It wouldn't go off a lot in my house. Anyway. No, sorry, hon. So here we've detected a bunch of points in both images, and these are going to be our feature points. The next thing we have to do, and just looking at this, it looks a little bit like a mess. We need to find the corresponding pairs. That tells us how we need to transform one image to the next. And then we can use those pairs to align the images. And if we do them in this particular example, you get something that looks like this. By the way, the seam has been left in here just to make it clear how that image is being moved. If you were actually splicing these images together, you would do something, sexy in order to make sure that those seams became invisible. Now, to do this detection and matching and alignment, there are a couple of things that we have to worry about. The first problem is, well, I can't possibly match points if I don't find them in both images. And remember, I'm going to detect interest points here and interesting points there and look for a match. So it better be the case that a point that's been found here to be interesting is also found over there. In this particular case, there would be no chance to match because I found some set of 4 points on the left and a different set of 4 points on the right. So what we need is what's referred to as a repeatable detector. If I run on this image, most of the points that I find over here as being interesting, I will also find over there, and vice versa. So that's the first problem, reliably finding them at all. The second problem is, let's assume that these points on the left are somewhere in the right. So I found here it's 4 points on the left, and then there's 4 points on the right. Which point is which? Okay, I have to do the match. The way we do that is what's referred to as using a descriptor. A descriptor is just what it sounds like. It's a description of a point, or of a feature to be precise. What I want are distinctive descriptors. That is, if I write down the description of each of these, so you can think of the description as being the name, right? So I want this one to be Bob, Ted, Alice, and George. That's mixing some metaphors from the 60s, by the way. Because if they all said George, 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 and this one says George, then I've got a French movie, and I don't know what's going anywhere, okay? But if this one says Edward, it better be that one of these things says Edward. Maybe if it just says Ed, I'll be okay. But my descriptor can't change that much of the same point in the two images. So that's what we talk about it being distinctive. Bob, Carol, Ted, and Alice. That's who it was from the movie, right? They have different names, but they also have to be reliable. So Ed might become Edward, but Ed doesn't become Francesca. All right. So feature points are used for all sorts of operations in computer vision. Image alignment, we talked a lot about. 3D reconstruction, motion tracking. I'm trying to figure out how either the object's moving or the camera. Object recognition. In fact, in a couple lectures from now, we're going to take some features from a bunch of different objects, take the features in our image, and figure out, it's this object that's in that image. All right. Database, indexing, robot. Features are used for all sorts of things, and that's one of the reasons why we have to talk about them in the class.
Here is a section of the Berlin Wall, photographed from two different angles. I've marked some candidate regions in both images. Select the ones that you think can serve as good features. Note that when evaluating the fitness of an image region, you're only considering the pixels within it. Let me get you started. This gray patch at the bottom left is pretty bad. This nose in the right image is fairly distinguishable. So, any region with two or more edges coming in at different angles is a pretty good feature. Like this fat lip that shows up in both images, corner behind the ear, base of this nose in the left image, green corner on the pink wall, also in both images, and this top section of the wall in this right image. The cropped portion of the eye is also pretty good. So is this tooth that shows up in both images, although it could be hard to match given other teeth that look similar. These two regions involving the cycle and cyclist in the right image are useful as well. However, they're missing from the left image. Now look at the remaining regions. This one with the vertical edge in the left image cannot be located precisely. Same for these two regions with horizontal features. Also, this diagonal could be anywhere along the wall. And even these two with slight curvatures are no good. They could be part of larger curves and would be hard to localize. So, what makes certain image regions good for feature matching and not others? Think about any common properties you can see. How would you define these mathematically?
What makes a good feature? So here I have a picture just as an example. The first thing is, it's called repeatability/precision. The same feature should be found in several or multiple images of the same scene. Now, of course, these aren't all the same picture, because if I gave you 15 copies of the same picture, this would be a really boring class, all right? These are actually different pictures of the same scene, so things change a little bit. But despite those changes, I want to get the same points being identified, and that's repeatability. And also, I'd like it to be the same point. right? So there's this little red dot on top of the camera. There's one over here too. I wonder which one I'm looking at. See, I'm going to make Megan cut back and forth in her video. Okay, the little red dot. So that dot's a pretty good feature because there's only two of them that I'm looking at here, so I can find both of them, and the matching will probably be easy to do. And then they're very precise. That is, I'm not going to drift around. I'm going to be able to find right on that dot. The next thing is salience or matchability. This is how distinctive the descriptor is. So each feature should be able to be described uniquely enough that it's easy to find it, right? So if I'm looking at a bunch of white dots on a black wall and they're all the same white dot, that's really a problem, because that's the George problem, all right? Everybody's named George. I can't find anybody. I just quit and go home, all right? So you like to have a description that's different about them. Compactness and efficiency. Another way of saying this is don't get carried away. You remember when we talked about computing the fundamental matrix, we said, well, I only need 8 corresponding points, but I mean, maybe having a dozen or 20 of them might be better. Maybe even 50. But 50 is much smaller than the number of pixels in the image. So what I would really like to do is, in general, I don't want to have a feature everywhere, although in this picture there's a lot of them. But you see, even here, it looks like there's a lot of them, but I don't know, maybe there's 100. But there's tens of thousands of pixels here. So that's what it means by being compact and efficient. And finally, locality. Locality is not what you think if you think locality means exactly knowing where it is. That was the precision. Locality means that the descriptor that I compute about the feature, the description, the name, is based upon information that comes just from a pretty small area around the feature. Now you might think that, I'd like to take a nice big area to describe it, because that'll give me a nice, very distinct description. That's like a first name and a second name and a third name and a fourth name. It would give me a very rich description. The problem is, and I'll try to find, oh yes, right over here. So I'm looking at the side of this. Now I hope I'm still in the feed. No, that camera moved. I'm looking. Okay, good. Thank you. So I'm looking at the side of the lens over here, and the problem is if I take too much of the lens to describe what's going on, as I move over here and I start to get occluded, a bunch of that neighborhood goes away. That's the same thing as when we had, a finger getting occluded a little bit by the other. So since I'm trying to find matching pixels from different views, and different views will cause a little bit of occlusion to change, I don't want the neighborhood that I used to describe to make the descriptor to be too large. And that's what locality means. It makes us more robust to sort of clutter and occlusion. So, believe it or not, that's the end of this first lesson. Why? Well, I want to cut your break a little bit. Actually, the real reason is the next lesson's got, shall we say, a modicum of equations on that, and to do this and then all of that, boy, that would be too much, so here we are. But the idea is that we've motivated what it means to be a feature, and a good feature. Features are being used to match one to the next. The two main properties that we talked about is repeated detectability. That is, if I find them over here, I'd like to make sure that I'm going to find them over in this image. And they also should be good for recognition one to another. That is, you can think of them as having a signature, and that signature should be distinct, right? Bob, Carol, Ted, and Alice, all right? But robust, right? So Edward might become Ed, but nothing significantly different beyond that. Turns out that this notion of being both distinctive and robust sort of works against each other, and we'll talk about that. So going forward, we're going to introduce about what it means to be a good feature, what it means to be a good interest point, and we'll break that down into two parts: detecting of interest points, and then characterizing the descriptor around those interest points. So sharpen your lead pencil. You guys even seen lead pencils anymore? Don't use a lead pencil on your iPad. It's probably a bad idea. And we'll do some interest point operators and how those function mathematically. Welcome back to Computer Vision. Today we're going to talk about finding corners, which might not feel like the most exciting thing in the world, but actually it is fundamental to a whole bunch of computer vision. Last time we talked a lot about the notion of features, and features were sort of locations in the image that you could find in multiple images so that you could match them, whether you were doing essential matrix finding or some other reason or some transformation. And we talked a little bit about what makes a good feature. So here was an example of some feature points. The first thing that makes a good feature is simply repeatability / precision, but really repeatability meaning if I find you in the left image, I better find you in the right image. Or if I have a sequence of images that I'm trying to line, I want to find that same feature point. I want to detect it as a point in as many of them as possible. The other thing is that I should be able to be sort of precise in my description. We'll talk a little bit more about locality in a minute. But the idea is that, this is the point. I find it every time, and I find it more or less in the same place with respect to the scene. The next thing we said needed to be important about a feature was the saliency or the matchability. And what we mean by that is that it should have a description that's distinctive. So when I find it in one image, when I look in another image, there aren't a lot of other points that might match that first image. The description should be distinctive. Something that we sometimes forget is that one of the reasons we're doing this, finding these features, is that we're going to use this, I think I used the term constellation of features. This collection of features is going to stand in for the image. So if you remember for fundamental matrices, we needed 8 points, although a dozen or more is better, 20. But the idea is that this is a number much smaller than the number of pixels. So compactness and efficiency says we should find good features, but we should not find a bazillion of them, or even half a bazillion. We should find enough, but not too many. How's that for a technical description? But the idea is that you're finding enough, but it's much, much less than the number of pixels. And finally, locality. And locality means that the description of the feature is dependent upon a neighborhood, but not too big a neighborhood. If you remember, one of the reasons we said that is that if the neighborhood is too big, then if I change my viewpoint a little bit and something is occluding part of that, even though I can still see the feature, the neighborhood might have been partially occluded, and then the feature might not be detected anymore or not described the same way. So locality means that I want a descriptor based upon a region around it, but not too big a region. All right, so fundamentally, in terms of what makes a good feature, we need to talk about finding one and describing one. And today, we're going to talk about the notion of finding these features, sometimes referred to as interest points. And these are going to be defined to be the points in the image that would likely make good features, that is, ones that satisfy all those criteria we just talked about. So let's start thinking about an image pattern. And imagine you're looking at a large black square against a white wall. Okay? Would the middle of the square be a good interest point? Megan, what do you think?
Yes?
Wrong. No. Look, remember one of the things we need to do is be able to precisely locate this? Well, in order to try to find the middle of some big square, there's like nothing there. It's all black. I wouldn't know where to land. Okay. Well, what about along the edge? Would a point along the edge be a good interest point? Megan, what do you think?
Yes?
No! Look, okay, so if my edge was vertical, we're going to do this in a minute. If my edge were vertical, I could tell which way to move left and right. But as I move up and down, nothing would really change, right? I just have black on the one side, white on the other side, and this edge in the middle, and I wouldn't be able to tell where that point lands. Okay, you ready, Megan? 2 strikes. What about the top left-hand corner? Would that be a good point?
Yes.
Yes, she got it right. Swings and hits a home run. Well, a triple. That seems pretty good, right? The idea is that I know exactly where that point is. If I told you go point to the top left-hand corner, you'd know where it was. Whereas if I said go point to the middle of the square, the exact middle, you'd look at it and say, I don't know. You'd have to get Megan, and she wouldn't know either, and she'd say, oh, I'm sorry. Anyway, okay, so let's take a look at this. All right, so this really is the basic idea of corner detection, all right? So here I have a black, sort of zoomed in on a black kind of rounded square against a white background, where this brown little square is, right? I could move that square up and down or left and right, and basically the pixels underneath that square wouldn't change very much. That's what's referred to as a flat region. That is, that there's no change in the intensity. Well, here's our edge. Okay, so now we've put our square over the edge. So what do we see? Well, it's the same thing we talked about before. Now I can know about moving left and right. I would know exactly more or less where that edge is. But if I were to move up and down, okay, I wouldn't be able to see any difference because there would be no change. So finally, what do we get to? Aha, we get to corners, okay? And the idea is that in the corner, basically because I have gradients in more than one direction, no matter how I were to translate that square, the pattern underneath the square will change. And so I can know when I've lined up exactly where I was before, right? So there's this idea that we need the gradients to have more than one direction. So this basic idea of finding corners, in thinking about it this way, I don't know if I would say it was first introduced, but I'll say that it was most well-known introduced way back in 1988. I know some of you guys were like in diapers, and some of you were a dream in your parents' eyes, and some of you were a nightmare in your parents' no, whatever. It's a long time ago, all right? And the picture here down below is just showing you sort of a mess of corners, and they don't all look like corners, but there are places where the gradient varies. And it was created, this paper, the Alvey Vision Conference is what later I believe became the British Machine Vision Conference, and it was done by Harris and Stevens. Now, if you ask anybody about the corner detector I'm about to tell you about, they'll tell you that they're Harris corners, because that's what everybody remembers. I know an awful lot of people in computer vision. I don't know who Stevens is. So this tells you something, that if you're doing a paper with somebody, try to get your name first. Unless, of course, it's your advisor and he or she's paying for your education, in which case then, you know. But anyway, it's actually Harris and Stevens, and you can impress somebody by saying Harris and Stevens corners, but it's Harris corners. All right, so let's learn about Harris corners. So Harris corners are based on an approximation model and an error model. And here's how we do. Let's assume that we've got an image I, and right here, right? And I is the intensity image. And what we're going to do is we're going to say, if I shift that I by a little bit, by a U and a V, and I were to sum up the square over some window, how much error would I get? Okay, that's the game we're going to play. So stepping through that, I is our image intensity, so I of xy is just the original image. The U and the V is some small shift. So if I were to pick up my window and move it over a little bit, I would now get some different image, just shifted by a little bit. I subtract them and square them, and then I'm going to sum them up over some window. Okay, so the window is going to be some area around some point. So that's written here as W of xy. The total value here, E, is sort of for error. You really can think of it as sum of the change, where E for error, energy. But the idea is that we're going to sum it up around that window. Now, of course, your window can typically be a square window, like in my house, or if you wanted it to actually work a little bit, or on a slow computer, you make it be a square window. But if you actually want to weight the pixels near the point you're thinking about more than the pixels that are far away, you would use a window that falls off in intensity. So like a Gaussian window would be an example. So typically, your windows can be square if you need to be really fast, or smooth if you need to be really good. So are you fast or are you good? So now we can start to graphically illustrate this. So on the left, I have an image, I of xy. And on the right, I have the new function E of uv. Okay, so remember, E is the error. Okay? And what we're going to do is we're going to put 0, 0 sort of in the middle, right? So this goes plus in U and minus in U. This will be plus in V and minus in V. All right? So what if I just leave the square right in the same place? What if I make U and V be 0? How much error am I going to get? Well, none, okay? And so E of 0, 0 is 0. I'm just subtracting the same image from itself, and that's what this E00 is meant to show. Oh, and by the way, just showing you, this little pixel here is black. Why is that black? Because that's 0, right? There's 0 error, E of uv, right? Error, because it's a sum of squares, can only become more positive, right? So at 0, 0, it's going to be an error of 0. So now, suppose I move my window just a couple of pixels, like 3 in the U direction and 2 in the V direction. Now my error is going to be whatever it is, right? And over here, right, you'll notice this is now a gray value, right? Because the value has gotten higher, right? So the error grows as I move away. And just think for 1 minute, suppose that picture were perfectly gray. Every pixel was the same value. That error would be 0 at the middle, at 0, 0, and as I moved it, it would still be 0. So that should give you some idea of where we're headed. We're looking for points where, as I move in UV, I get this nice change no matter how I move in UV. Got it? Cool. So what we want to do is, we want to figure out, we want to model how this error function changes for small shifts. So we're not going to move U of 97 pixels, No, we're going to move maybe even just a fraction of a pixel or a little small shifts right near u and v being 0, 0. That is around no shift at all. And of course, what we'd like to see is that we get a significant change even for a small shift. That would tell us no matter how we move in u and v, and that would tell us that this image is going to change as I move around, and maybe it's corner-like. So how do you predict the value of a function for small shifts? Do you remember this? Do you remember this? Oh yeah, calculus. Taylor expansions? All right. We're going to do a second order Taylor expansion of e of uv, that's our function here, around u and v being 0, 0. And the second order means it's going to be a quadratic approximation. All right, so strap in, because we're going to go through the math of doing that, and it'll get us to a point where it's very easy to compute whether the neighborhood around a point feels corner-like. All right, so you may not remember everything you need to know about Taylor expansion, so I'm going to write this out. So back when you first took calculus, this was the equation of a Taylor approximation, where we say that the value of a function of some small delta near 0 can be approximated by the value at 0 times the first derivative times delta x times the second derivative of delta squared x, half of that. That was the Taylor approximation. I'm sure you all have that tattooed somewhere on your body. All right. So it gets a little uglier when we do things in 2 dimensions. Remember, it's u and v. Okay? And we're going to write that out for this expression, this error of uv function this way. You ready? Okay, don't panic. What we're saying is that the error function uv for some small uv's near 0 can be approximated by the value at 0, 0, the first derivatives times the uv, so that's like this df of x times delta x, except now we've got it in 2 dimensions. So we've got the gradient in the u dimension plus the gradient in the v dimension, plus we have this quadratic term, and in vector notation for 2 dimensions, that quadratic term is written like this. So these are our second derivatives, uu, vv, this is uv, uv, and we just matrix multiply times the uv vector. Hopefully this is somewhat familiar to you from your vector calculus. If not, it's just true. So now what we're going to do is we're going to step through, bear with me, this whole second order Taylor expansion about uv of 0, 0. By the way, you guys should appreciate that I am not writing this. So you actually could read it, and there'll be PDFs presented of some sort so that you can get it from there, or you can go to Rick Zalisky's book. It's all there. But believe me, you don't want me to write this. You just want me to be humorous and lighthearted. All right. So here we have our Taylor expansion written just as before. So we're going to knock these derivatives down one at a time. We're going to start with our first derivative, right? We have to do the first derivatives and the second derivatives. So the first derivative we're going to look at, the first derivative we're going to look at is with respect to the u direction. Now u is the offset in the x direction. Okay, just remember that u is the offset in the x direction. And we're going to take the derivative of this function, e of uv, with respect to u. Okay, let's see, well, we've got the square term here, so that gives us this, we raise it to single power instead, and then we have to take the derivative of the inside term with respect to u, and let's see, there's no u's in there, that's go away. So there's a u in here, so I have to take the derivative of I of x plus u, y plus v, with respect to u. Okay? Not me, you. Okay, anyway. Well, remember, u is in the same direction as x. So the derivative of the image in the u direction is the same as the derivative of the image in the x direction. So I need the image gradient, I sub x. Got it? Good. I'm not going to do v. V is exactly the same thing, except instead of x's, you get y's. Now what we do is we're going to do the second derivative. So we're just going to take the derivative of this with respect to u. Well, there's 2 parts here, right? We've got this part, and we've got that part, right? So the derivative of a product is u times dv plus v times du, remember? Yes, 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 yes. Except u's and v's is a terrible choice because we have different u's and v's. But basically the derivative of the first times the second plus the derivative of the second times the first, what is that going to look like? That's going to look like this, okay? So we take the derivative of the part that's the image and multiply it, so that just gives us this twice. And then the second one is we take the derivative of the derivative and multiply that by the original. That gives us this second derivative. Okay? The math's pretty easy. You can work it out. This is the E with respect to UU term. All right? So we've done the first derivative, the second derivative, U and V are the same. So the only thing left to do from that matrix, we had EUU, EVV. We need the cross derivative. And that just looks like this, where we take the derivative of the previous one, of U with respect to V now, and we get something that looks like this. And you'll notice that this has the gradient in Y, the gradient in X. Remember, X is the same direction as U, Y is the same direction as V. And it also has this cross derivative. We haven't talked a whole lot about the cross derivative, and in fact, we're not going to talk even more today about the cross derivative, because later we're going to make it go poof, go away, so we won't even think about it. So now we have our first derivative, U, V is the same. Our second derivative, UU, VV is the same, and our cross derivative, right? Right. So here they all are in their incredible glory. All right, so this equation is ugly, but we're going to be able to make a bunch of it go away. And the reason that we're going to be able to make a bunch of it go away is since we're going to evaluate it at U and V equal to 0, 0, we're just going to make all these plus U's and plus V's everywhere be 0, 0. Okay? Remember, we're evaluating our derivatives at 0, 0. So all of these terms that have the plus U, plus V, the plus U and the plus V go away, and you get something much simpler that looks like this. Now, that still looks kind of ugly, okay, until we start to realize that a lot of this stuff goes away. So first of all, what is E at 0, 0? What is the error I get if I don't slide the thing at all? It's 0. Great. Next, I've got this funny little term here. It says I of xy minus I of xy. What is that? You betcha. 0. Okay? And here it is again. 0. And notice this 0 is the one that's multiplying the second derivative term. And what about down below? Another 0. That's the one that's multiplying the cross derivative term. So when I get rid of all of the stuff that equals 0, my equations become very, very simple, and they look like this. Okay? My main function is 0. My first derivative components are 0, and these components, which go in the matrix, they are just these simple terms here, okay? And you'll notice that the only thing in here is first derivative with respect to x times first derivative with respect to x, first derivative with respect to y times the first derivative with respect to y, and the first derivative with respect to x times the first derivative with respect to y. Say that 7 times fast. There are no second derivatives left. So getting rid of all my erasures, we take that bottom part, we shove that into the top part there, because that's the only thing left that's going to be non-zero, right? Because this is all 0 and this is all 0 because of these zeros. All right? So when we do that, what does our equation look like? It looks like this. All right? So the only thing we have left is that the evaluation of that error function for a small u and small v is approximately, remember it's a Taylor series approximation, is approximately this function. Okay? And remember, no more second derivatives. They've been killed by multiplying by these zeros. We just have the squares of the first derivatives and then the product of the two different derivatives. That's still pretty ugly. We can make that look even nicer. All right? Here is a very simple, beautiful way of writing this, that this quadratic approximation, so quadratic, remember we're just looking at the square terms of EUV, right, can be written in matrix form as UV times this matrix M times UV. This, you can think of this as UV transpose. All right. Where M is the second moment matrix written down here. Okay? Again, what it has is it's the weighted sum of the squares and of the product of the two different derivatives. It pays to think a little bit more about this M matrix because we're going to do it even more in a minute. All right? So here I just copied it over, and for a moment, it's kind of a joke. For you guys are physics geeks, if I say for the moment and we're talking about the second order matrix, you realize it has something to do with the moments of inertia? Never mind. Okay. I'm going to write that M matrix without the weights at the bottom. Okay? And when I write it that way, you can see that this is just the sum of IXX, sum of IYY, and the cross sum. That can just be written as the sum. This is referred to as an outer product. Right? So it's the outer product of the single gradient. Okay? That's what this says. One of these is just the outer product of one vector. It's a 2 by 2 matrix, but it's an outer product of one vector. From your linear algebra, you'll realize that's only a rank 1 matrix, right? Because let's just take the columns. The columns are just a multiple of Ix, Iy, and each column is a multiple multiplied by a different scalar. So when the two columns are scalar multiples of each other, it's not a full rank matrix. So this 2 by 2 is actually rank 1. Okay? That's what it says here. Each is a product of rank 1. And then, of course, this thing is going to be summed over all of the points within the window. So what's it going to take for this matrix to be full rank, for this to be sort of a well-behaved ellipse? We would actually have to have gradients in different directions over the window to be summing up a bunch of different rank 1 matrices, and that would get us to a full rank. So looking at that, we can think about it this way, all right? So the surface E of uv in this quadratic form is being approximated essentially by this quadratic or a sort of parabolic shaped form here, and that's just written the equations out. Now, let's think just for a moment if you were to take a fixed value of E, okay? So we're just going to pick some constant value, all right? So that would look like this, all right? And here I've written it two ways. I've written it sort of down below in sort of the elegant matrix way, which we're about to cover up because I like inducing pain. And the top way is just the algebraic expression of that expression equal to a constant. And what you can see here is, you might remember, this is the equation of an ellipse in U and V space. All right, so remember ax squared plus bxy plus cy squared equals d or something like that was an ellipse, and if the middle term, the xy term, was 0, it meant that the ellipse's major and minor axes were aligned with the x and y axis. Well, this is the same thing. This is just an ellipse in the UV space. All right, so we can draw that out like this. Okay, so here is different ellipses for different values of k. So you can think about that. The way we're approximating this whole surface is as a quadratic surface that gets bigger and bigger, and each different level is an ellipse. Okay, so that's what you get when you do this type of second-order quadratic Taylor expansion of this function. So we can look at this ellipse a little bit more carefully. Okay, let's first consider the case where the gradient at every point in the image is either horizontal or vertical. Sorry, not in the image, in the window. So at each point, it could be horizontal or it could be vertical, but it's not going to be slanted, okay? So some places it'll be horizontal, some places it'll be vertical, but it's never, both Ix and Iy are never non-zero at the same time. Well, that would mean that these terms would always be 0, right? Ix times Iy, right? So that would look like this. And I'm writing this as lambda 1, lambda 2. These are the diagonal terms. The off diagonals would be 0. Now, that's a nice full rank matrix, right? Lambda 1, lambda 2. Except if one of those were 0, it would not be a very good it would not be a full rank equation, right? So for example, if the Iy squareds were all 0, it meant there was no gradient in the y direction, only in the horizontal direction. That would mean that my matrix would only have one of these values, and probably that's not a really good corner, right? Because if I only have, say, a gradient in this way and not in that way, then I can slide up and down as much as I want. So something about these numbers tells us how good a corner the location in the image is. Can you smell the algorithm that's coming? It's not me, it's Megan. In fact, I'll write it just this way. If either of those lambdas were close to 0, this is not a corner. So what we want is we want to look for locations where both of those are large. Now, for those of you who remember from your calculus and your linear algebra, of course, we can take this second order matrix, this ellipse, and what we can do is we can diagonalize it through a rotation. And remember we talked about singular value decomposition? Well, this is not exactly that, but it's quite related, where basically what it says is we can think of M, which is that special matrix, as being sort of rotated or unrotated by R, then it's a diagonal matrix, and then it's re-rotated. The axis lengths of those ellipses, okay, how big those ellipses are, that's determined by the eigenvalues, these numbers, of that diagonalization, and the orientation of the ellipse is determined by that rotation. So here I'm drawing that like this. So remember, this is a particular ellipse of constant E, constant error. So for places where it's a very narrow ellipse, that means that the E changes quickly. I didn't have to move very far for the E to get to that value. Whereas the places where it goes very slowly, okay, I have to move a farther distance in order for that value to change. And you see how it says it's 1 over the square root? So remember, if that lambda were 0, okay, that would mean I'd have to go in infinite direction. That means it doesn't change at all as I move in that direction. So what I'm telling you here is that the eigenvalues of that M matrix are indicative of the cornerness of that matrix. That's pretty cool. So it turns out Harris figured this out, and they figured out a really simple way of thinking about this. Here's how we're going to do. The idea is that we're going to classify our image points based upon computing that Harris matrix and looking at some measure that's a function of its eigenvalues. And the idea is that in a flat area, both of those eigenvalues would be very small. In fact, if it was perfectly flat, everything would be 0 because the gradients were 0 everywhere. And that would mean no matter how I moved, nothing changes. So it's a terrible corner. Likewise, if I have just one of the eigenvalues large, that means there's some direction that it changes quickly. So if I move in that direction, I know things have changed. But if it's 0 in the other direction, I can move as much as I want. Remember, that's what happened along an edge. So when one eigenvalue is much, much bigger than the other, then you're along an edge here. And when is it a corner? Well, when both of the eigenvalues are large. And we'll say that it says here that they're approximately the same magnitude, just that they're both big enough and that the ratio between them should not be terrible, right? Even if they were both large, but the ratio between them was 10 million, then probably your code was wrong. If they're moderately large and your ratio between them is still pretty big, then you have to worry because it means one gradient is much, much more dominant than the other, and maybe the noise is affecting finding of the corner. So you want them to be approximately the same magnitude. So you might think, great, that means all I have to do is find the eigenvectors and the eigenvalues, right? Right. Guess what? You don't even have to do that. This is what was so good about the Harris thing. You have to remember something from your linear algebra. And by the way, I have to look this up every time, so if you don't remember, that's okay. One is that the determinant of a matrix, remember the determinant of a matrix? That's actually the product of the eigenvalues. Okay, so lambda 1, lambda 2, multiply them together, that's the determinant. With the 2 zeros in there, it's easy to see, it's a little hard to see in the more general case. The other thing is that the trace of the matrix, right, the sum of the diagonals, is the sum of the eigenvalues. So the determinant of a 2 by 2 is trivial to compute, right? This minus that, or however you like to do determinants of 2 by 2s. Trace is easy, sum them up. And the Harris operator was just to compute some function r. You take the M matrix, you take its determinant minus some constant of the square of the trace. And I'll tell you that empirically, the constant was some small number, 0.04, 0.06 written here. Exactly how things scale depends a little bit on the way you do your gradient operators and pixels. Okay, so it's the determinant, which is a product, minus the alpha trace. So the real equation of what you're looking at is right there. Okay, so taking a look at lambda 1, lambda 2 minus alpha times lambda 1 plus lambda 2 squared. Let's think about this. R depends on the eigenvalues, but we don't actually have to compute them. And that's great, because even in the 80s, you didn't want to compute your eigenvalues, maybe, I don't know. But the idea is that you compute a single number, all right, really fast, all right? So we've already said that R is large for a corner. And why is that? Well, if they're large, then both of the L1 and L2 are large. Their product is even larger. And if you take the squares, you know, it's L1 squared plus 2L1 L2 plus L2 squared, subtract it off. Yeah, but you're subtracting off alpha of it. It's a small amount. Okay, so it's still going to be large. But if only one of the L's is large, then this term goes small, whereas one of these terms is large, so the R value is negative. Okay, so you can measure the R value, and it's negative along an edge. So R is large for a corner, it's negative along an edge, and if the magnitude of R is small, basically that means that everything was small, right? So L1 and L2 is small, everything there is small. Well, that's the flat region we were talking about, right? None of the gradients have any magnitude to speak of. So let's take a look at this working. Here is some images taken from, there's something called the MPEG flower garden sequence. It was used for demonstrating certain kind of image processing algorithms. It's just convenient here. So the first thing is, let's take a look in a low textured region, all right? So there's not very much going on there. The gradients there have very small magnitude. And what's being shown here, both as an image and as a plot, is how does that error function change as I move around in U and V. And what you can see is there's no sort of obvious peak anywhere, positive or negative in here, to say that that's the obvious place for where you would want to find a feature. And remember, we're looking for that. Now let's take a look at another region. So here we have a point that's on this edge, that's where the roof line is, okay? And you'll notice that we have this ridge here, okay, of low error. And that's sort of represented through here. And by the way, in this, just to make the pictures easier to understand, the bright thing here is good and black is bad. And you don't want to go this way, but going along this way, you don't know exactly where your corner is. So let's take a look at sort of another patch, another place. And here we are right in the middle of the flower bed. Now, both of our gradients are large. The gradients are large in many different directions, so we have a large L1 and a large L2. We get this nice peak down here, and that's shown as this nice peak here. The idea is that this would have a nice large R value, Harris corner R value, that would find you, that says, you know what, if you give me that point, and I'm looking for that point again in another image, any small motion is going to give me a big error change. So that's a good suggestion for where a corner might be. All right, so here is the simple Harris detector algorithm, courtesy 1988, still used today a lot. We're going to talk about different versions of it going forward when we talk about scale and stuff, but for now, we're just going to talk about this. And here's the basic algorithm. You first compute Gaussian derivatives at each pixel. Okay, so remember you need this Ix and Iy, and we've talked all about how to do derivatives, where you take the derivative of the Gaussian operator, apply that, and you get back your nice image derivatives. Then you compute that second order moment matrix M, that M matrix that we're talking about, and the recommendation is to use a Gaussian window so that you weight the points near the middle more than the points that are further away. And then you compute that R function on that M matrix. Remember, you have a different M matrix for every point in the image, right? Because you take a little window around a point, compute the moment, compute R, move on. So you have one for every point in the image. So you get all these R's, you're looking for high values, you threshold that, and then, and we talked a little bit about this when we were doing the edge detection, you do what's called local non-maximum suppression, right? So I might have I might be a strong R value, but if there's a stronger R value next to me, throw me away and keep him. Sorry about that. But the idea is that you're looking for local areas that have the highest possible R value. And like I said, this was presented originally in this paper in '88. Just to show you some examples, so here we have two pictures. I wish I knew where these pictures came from. These are like so hysterically cheesy. Two pictures of a toy giraffe. You'll notice that a couple of things. First of all, obviously the orientation has changed a lot, but also the head has been rotated, right? So here it's on the side, and here he's facing you, and so things have shifted a bit. The feet are a little different. Of course, the entire object has rotated, and the intensity has changed. So there's been quite a bit of change done to the image. So here we go. We compute our derivatives, we compute our moment matrices, we compute our R functions, we plot them in MATLAB using a interesting pseudo-color color map, and you see this beautiful picture. And that's R everywhere, and the next thing you have to do is threshold that. So here are all the points that R is above some particular threshold. Then we do that trick of the non-maximal suppression, right? So we only keep points that are locally higher value than anybody else. And this is probably pretty hard to see. Megan helped a little bit by putting this line down the middle. So there's this constellation of points on the left and the right. You know, if I look at that, I can't really tell it's a giraffe. But what I can do is I can show you those red points on the actual giraffe itself. There's a giraffe, right? Yeah, it's kind of a weird giraffe. Somebody's fan. It's like a creepy giraffe. It's like always smiling. Anyway, all right. And here you can notice that we've found a bunch of points repeatedly. So, for example, on his nose, on the right nostril there, there's a point right there. Well, guess what? We found the same point right there. So if I wanted to see how the head was changing, right? Points on the ears are there, okay? Points on the back of this spot here are there. Points on the bottom are there. Now, of course, all these points, they're not there. Well, of course not. There's a specular reflection in the left image that's not in the right. That's okay. Harris couldn't possibly know about that. The point is, that we reliably found many of the same points. And if you remember what we were talking about for doing this interest point or key point detector, we need a reliability and a precision. We have to find the same points and find them in the same location on the scene or in the scene. And that was what would make a good feature. I should mention that there have been other attempts at, other pieces of work on finding corners. In fact, she and Tomasi did this nice work on cornerness, and it did something different looking at the lambdas instead of using that R, and found local maximas. And I will tell you, if any of you who use OpenCV, they have something called OpenCV Good Features to Track. It's a function. It finds you points in the image that are good points to track. How does it work? I'm pretty sure that's the Shi and Tomasi version of this. It's still based upon the same moment matrix. It's just a different use of the eigenvalues. And there's reports that maybe it's a slightly better way for things that are undergoing certain kinds of deformations. There was another one, 2005, Brown, Selinsky, and Winder, and I write this one because I've stolen so many of these pictures from Rick Selinsky's book. I feel like I have to put this in there. It again looked at eigenvectors in another slightly different way. And there are other types of corner detectors. That ends our very long lesson on Harris corners. I'm hoping Megan can do some like video magic. So you've actually just seen 3 magnificently edited, cut tight. I hear she's friends with John Williams, so there'll be a score in the background. Anyway, but this notion of variation in gradients is very important in general. It's used for feature detectors, but this notion of gradients varying over a window will be important when we do other issues having to do with motion and stuff like that. But for now, we're just thinking of it as doing point detection. And in the next couple lessons, we're going to take a look at some of the properties of this detector, and then we're going to build some descriptions, some descriptors around those detected points. Are you tired? I'm tired. All I've got to drink is water. I hope you can do better. Welcome back to Computer Vision. Today we're going to continue our exploration of feature detections. You remember last time we started talking about interest points, ways of detecting locations of the image that we can get back to, and we focused on finding corners. And why corners? Well, as we talked about, corners had this nice property that if you put a little operator over an area that was a corner, whether you moved it left or right or however you moved it, you would see a pattern changing. And that was not true if you were over a flat region or over an edge. Over an edge, if you moved in the direction parallel to the edge, you couldn't see any change. And we derived some nice mathematical formulations where we talked about the error as you slid things around. We said how the error was 0 before you do any sliding at all, and that as you move, the error changes a little bit. And what we did was we said, well, can we build a model or can we approximate that error by looking locally at the structure of the image? And then we wrote this out as a expression really just involving what's called the second order moment matrix, that moment matrix being the sum of the squares of the first derivatives. So ix squared, iy squared, or ix times iy. And even though it was a second order moment, there were no second derivatives, right? No I sub xx, because those all went away when we evaluated around u and v being 0, 0. You can go back and review that lecture. And then we talked about how Harris and who? Harrison, who knows? No, Harrison Stevens did this thing where you derive an operator based upon that little matrix, based upon its determinant and its trace, and you could use that to find good points. And we showed this horrible giraffe image, and we said, yep, the thing seems to work pretty well finding those points. What we're going to do is now we're going to look at some properties of the Harris detector and actually of one or two other ways of detecting some interest points. Remember, the reason we're doing this is to find points that are going to be our feature points. So let's start with rotation. Okay, if I've got an image, so we have here a little notional corner, and I were to rotate it, how would the Harris operator change? Well, remember that whole thing about the ellipse rotating? Well, the ellipse would rotate, right? But it would be the same ellipse, right? Because the variations in the gradients would be the same over the window. The whole thing would have rotated. So basically, the Harris corner detector is invariant to rotation. That's cool. You don't have to take my word for it. You can take somebody else's word for it. No, you can actually study these things empirically. Right? So the idea is you take some picture, you find some corners, and then you change the picture somehow, right? So maybe you rotate it a little bit, and then you find some corners again, and you measure sort of this repeatability, right? So the number of correspondences that were found versus the possible ones that you should have found. That is, how repeatable was the ability to find the same corners? And as you can see here, as they varied the rotation of the picture all the way up to 180 degrees, you've got pretty good reviews. By the way, imp Harris is improved Harris. But you can see that both Harris and the improved Harris are pretty invariant with respect to rotation. By the way, these plots come from this very nice paper from Cordelia Schmidt and folks there. And in fact, here it is showing you. It's from the International Journal of Computer Vision. I put these sort of basic sources in here just so you can see where some of this stuff comes from. And if you're interested in computer vision, I encourage you to take a look at what these papers actually do to get a sense of how this stuff got derived. What about changes to intensity? Right? I change the intensity somehow. What happens to my corner detection? Well, it turns out that it's mostly invariant to additive and multiplicative intensity changes. So as it says here, look, the moment matrix is just made up of IXs and IYs and the products of them. Well, IX is the derivative in X, the IY the derivative of Y. If I add a constant to my image, nothing changes. My derivatives are the same. So it's totally invariant to changes in intensity shift. I just add a value. What if I multiply everything? Well, when you multiply an image, you multiply the gradients, right? Well, when you multiply the gradients, you multiply the R value. And that's what's shown here. Here we have an R function with certain peaks that were above a threshold, and if you were to scale the image by a scalar, you would just grow those peaks, all right? But the shape would be the same. And the only thing you have to worry about is, since you're using some threshold, maybe some points that were above the threshold or below, depending on whether you're going up or down, maybe they would now change which side of the threshold they're on. In practice, intensity variation, multiplication like that is not an issue. What about change to scale? Well, what'll be clear is it is not invariant to image scale. So here what we have, two different curves. Here I have my original curve like this, and here I've just zoomed out and I have a much tighter curve like that. And the little boxes here, those are meant to be the size of the window. And if you take a look at each one of these, all these points will be classified as being edges because essentially there's not much gradient in the directions parallel to the edge. But if I zoom out, this is now a very good corner. And so the problem is that by changing this smooth curve, by zooming out so the curve becomes tighter and tighter and tighter, it goes from being a bunch of edges to being a corner. So in general, the Harris corner finder, corner detector, is not invariant to scale, and guess what? The data prove that. Okay, here's another graph taken from a similar paper, and you can see that it falls off pretty drastically as you get to scale. In fact, even with just a scale factor of 2, so I just zoom in or zoom out by a factor of 2, I've already lost almost 80% of my repeatability. So it's really, really not invariant to scale, and we're going to have to do something about that. So let's just think for a minute. Suppose we wanted scale invariance. How could we do that? So to think about this, let's consider some regions. I'm going to use circles, it's easier to think about, of different sizes around some point. Okay? So here on the left, I've got a curve that is the zoomed in version of the curve on the right, and I've got some circles around this. You know, when I look at the part that's in this circle and the parts in that circle, I say, no, that curve doesn't really look the same. If I make the circle a little bit bigger, no, it doesn't really look the same. How about now? No, not yet. I say, oh, wait. Now, with this bigger size, this piece of curve looks a lot like this piece of curve. All right? So the regions of corresponding sizes will look the same in both images. It's not the same size. I call them corresponding sizes. It spans the same amount of the image. So the problem, of course, is we have to choose the circles independently, because I'm dealing with this image and I got to figure out what scale to do things, and I'm dealing with this image, I got to figure out what scale to do things, and I want it to be the case, the way the red circles are indicating here, that the scale I pick for the left-hand image is this nice big circle, and the scale I pick for the right-hand image is this small circle. So that's what we want to do. We want to be able to do this independently in the images. So how might we do that? Well, here's a solution, okay, and graphically it'll be a little bit easier to see. What we're going to do is we're going to design some function, okay, and it's going to be a function over that circle, and this is a little bit tricky. We're going to call it scale invariant, and what we mean by that is the function doesn't actually care how big the circle is. It just cares about, say, the distribution of the values of the pixels within that circle. So a simple example, not one that we're going to use, but it's simplest to understand, is imagine average intensity. Right? If I just take the average intensity over a circle, that function doesn't care how big the circle is. It's just going to compute that function over whatever size circle you give it. And in fact, if it were a constant gray value, if you kept making the circle bigger and bigger and bigger, it wouldn't matter. The function would stay the same. If you have a function that changes over different corresponding regions, then that function would go up and down as you looked over those different regions. And if I zoomed out of that thing, it would go up and down again, but now it would go up and down faster because as I grew my circle, I would be covering more of that picture as I move that circle out. Now, I know that was clear as mud, so let's take a look at a picture. All right? So imagine at a point, you compute one of these scale invariant functions, like average intensity, over a range of neighborhood sizes, okay? So we're at a single point, and we're computing this function f over different region sizes. And you'll notice that, well, it goes down, and then it goes up, and then it goes down again. So that's my function that I've computed over different region sizes, all right? Now, let's suppose in my next picture, I shrink the thing down by half. Well, now, as I compute that same function over the same region sizes, 2, 4, 8, 16, right, it's going to take the same shape, but it's going to get there faster, which is why this function is essentially just a squashed version of the one on the left. But it's the same function, just squashed. Well, what that means is, suppose we pick the maximum of that function. I'm going to call that S1 in image 1 on the left. And I take the same function, and I'm at some other point. I'm same function on point in the second image. If I were to take the maximum there, it would be a different size, right? Because that image had been squished in half. That would be S2. But these two neighborhood sizes would be covering the same region of the image between the two pictures. So they would be matching scales. So the important thing is, I do each one of these things independently. That is, I do this thing, and at this particular point, I find my maximum function, my maximum of the function. I say, that's the natural scale size that I'm going to use. Then I come over here, and I go to my other image, and I do over here, and I'm at some interest point. Remember, we found our interest points, and I look over all these different region sizes, and I say, aha, this is the scale there, and I compute that function, and magically, these two scales correspond. These are the same chunk of image. Here's a very nice illustration of that. Here's a picture of probably some beautiful church on the inside. Here it says white and gray in some church in some mountainous area of Europe, I'm going to guess. And you'll notice that there's a function here that we're computing as a function of scale, and here it is. And this is the maximum point. And this circle is meant to reflect the scale size of that maximum. Here we have that same image zoomed way out. Computing at this interest point, so we've got the same interest points. You notice that this interest point is just sitting at the top of this little chimney thing here. We compute the function again, and again we take the maximum, and that's going to be this circle. And the really cool thing is that this circle and this circle are the same components of the image. Those are the two scales to operate at. If we want to find descriptors that match, that's coming later. Basically, the scale of my detectors in one image should be big, and in the other image should be small. Also, the scale of my descriptors and my detectors. So I told you before that nobody actually uses average intensity. Right? So what will we use? Well, let's think a little bit about what it means to be a good function for scale detection. All right? Basically, what you want is you want to be able to find these maxima as a function of the region size. Okay, so it would be bad if for large variation of the region size, basically the function stayed flat. That would be bad. Another thing would be something that wiggled too much. There's only 3 wiggles here. Imagine there were a lot of wiggles, because we'd like to find a maximum, and we'd like to find really just, one or a really key maximum that we can pull out. So, this becomes your ideal function. It's sort of a cartoon of the function there. So the functions that people use, what you want is one that, responds nicely to contrast, right? Because the idea is, you're going to have edges at some scale. Oh yeah, remember that? Right? So edges occur at some scale. And if you were operating at the right scale, you'd get this nice sharp contrast. And if you were, as you got away from it a little bit, it would fall. And if you got too far, it would fall down on the other side. So there's going to be something having to do with contrast, or finding points of high contrast. What are points of high contrast? Remember edges? Okay. So in fact, some of the detector operators that people use are just applying, remember kernels? And these are the kernels like when we applied differential operator kernels. We just apply a kernel to the image and use the output. Now, one that people sometimes use, and we actually talked about this Laplacian of Gaussian. When we talked about edge detection, we said, well, in the first derivative, there is 2 directions you could do. You could do an x and a y. And then we said, well, if you have to worry about the second derivative, there's all sorts of challenges. But we mentioned something called the Laplacian of Gaussian, the Mexican hat operator, right? And this was this one, and the equation is written here. I actually pulled out my own MATLAB here and made a little 3D plot of what it looks like. And here this shows you. It's an operator which essentially is a second derivative operator. And we talked about zero crossings. Go back and review the property of what we did on edge detection, and you'll see it there. So that's the type of operator that you could use. Now, something that we didn't really talk about, instead of doing this whole Laplacian of Gaussian, which involves these sort of annoying second derivatives, there's a cute little trick you can do, and that's called a difference of Gaussians. And that's what's written here, is basically if you take one Gaussian and you subtract from it another Gaussian with a slightly different, or some factor different sigma, you get a curve. And what's plotted here in the red is the difference of Gaussian, and in the blue is the actual Laplacian. And you see that the values are almost the same. So for doing the work here, it's a lot easier, since you're computing these Gaussians anyway, to just subtract these. One of the things also is that these Gaussian, the difference of Gaussian and Laplacian is circularly symmetric, so it's totally invariant with respect to orientation. Okay, so as you rotate your image, nothing changes. And it says that it's invariant to scale. What that means is it's just like it's a scale invariant function before. If I blow up the function and then I make my operator that much bigger, I'll get back the same value that I had before. The way we do that for what's called key point localization, and key point and interest points are used similarly. Key point was the term used by David Lowe in SIFT. We'll talk about that in a minute. Here is the general idea. We want to find robust extremas. So maximums, by the way, you can also find minima. So if you remember for the Laplacian, it goes through 0, goes positive, negative. So if you took the absolute value of that, say, the square, the value that's 0 is a good point. Anyway, you want to find robust maximum minima in both space and scale. So that's what's drawn here. We haven't talked a lot about scale space, but the idea is, I have an image, and then I could filter that image again, and I could filter it some more, and you can think of it as a coarser and coarser scale. And I have some point, and you can think of that point as having neighbors to the left and right, and you can also think of that point as having neighbors up and down in scale, and that's referred to as scale space. A specific way of using that scale space was suggested by David Lowe in the SIFT paper. But at that point, there was a specific suggestion of do this difference of Gaussian pyramid. What I mean by that is you do it at different scales and over space to find maximum values in all those. Now, sometimes you might land along edges. Okay, so you're on a maximum value, but it's really just the maximum along an edge. So what you have to do is you have to eliminate the edge points. In fact, if you recall, we first introduced Laplacians of Gaussians to find edge points, right? Even though it was a circularly symmetric operator, you were able to find these edges. So from way back, from the Harris, we said, well, edges aren't so good for finding specific locations. We want it to be more like a corner. So basically what you would want to do is you would want to find points that have these extreme values, then make sure that thresholded, that they were extreme enough, if you will, and then make sure they're not edges. So here was a particular method by which it was done, and I show you this so you can take a look at the results in a minute. Basically, what was done was you take your image and you deal with it an octave at a time, and an octave is a doubling. So what you do is you make it blurrier and blurrier and blurrier and blurrier. Then you take half, then you reduce that down to half the size and make it blurrier and blurrier and blurrier and blurrier. And what you do is you subtract these off to get your difference of Gaussian images. Then within each one of these Gaussian images, you're going to compare a pixel. And in fact, if I go back to this picture here, I'm going to compare this pixel to each of its 8 neighbors, and each in the same plane, and there are 9 neighbors above it and 9 neighbors below it. And if you're a maximum of that, you're going to say, aha, I'm an extrema. So here you have a picture of Einstein, and each one of these is a different octave. It's cut in half, cut in half, cut in half. And then you can see we go from crisp to blurrier to blurry to blurry. It's probably the only time Einstein was fuzzy in his life. And then, just as we showed in this picture before, we can subtract, example, these two and get that difference, all right? Or we can subtract these two and get that difference, right? So these are our difference of Gaussian images. And then what we can do is we can take each pixel in one of these and compare it to its neighbors in space and its neighbors in scale. And when you do all of that, you can find the extrema, and it looks like that. So this is an Einstein picture with really bad dots, but some of those extrema might be higher than their neighbors, but not very high. This happens in Colorado. So you want to make sure that the contrast or that value is higher than a particular amount. So we say, aha, here are places with contrast. But we say, wait a minute. We said before that when we use Laplacian and Gaussians, we might have nice contrast, but it might be high just in one direction, so along an edge. So what do? We remove the edges, and voila, these are our detectors, okay? And what's important here is these are detectors that are robust with respect to scale, because we pulled out all the extrema at all the different scales. And this was David SIFT detector. So this can be written sort of like this. So for scale invariant detectors for SIFT, here we've shown that you're going to do difference of Gaussians in space and difference of Gaussians. You're taking all these different Gaussians, comparing them in space and in scale, and you're picking the maxima. And here's a reference from, again, the journal Computer Vision, where he talks about this. There is another approach that's quite related. It uses both things that we just talked about. First, you essentially do the Harris corner detection at lots of different scales. And then you also take a look at the Laplacian in the scale direction, and you find points that are the maximum in space in the Harris measure, right? That's like that non-maximum suppression, and are maximum in space, in scale, in the Laplacian direction. And this is sometimes called the Harris-Laplace detector. The paper here, ICCV, is one that's referenced. And I can show you, here's a nice little demonstration that with change of scale, that, well, first you can see the original Harris detector, in fact, does really poorly. That's what we saw before. The SIFT detector, that's the thing in the green line, that was the thing we showed you before, it does way better than the Harris detector, but along comes Harris-Laplace, and it does even better. And so you might say, well, of course we should use Harris-Laplace. I will tell you a lot of people do. I will also tell you that this graph comes from the people who invented Harris-Laplace. So, you know, your mileage may vary. What we've learned about today is how to deal with images that have large-scale differences between them. Frankly, if you have two images that are translated, rotated, made brighter, darker, etc., stretched a little, skewed a little, the scale may not matter as much. But if you had a large scale difference, then what you do is you try to find the same scale around the interest points by that scale invariant function, and you search for these maxima. All right. So where are we? So we know how to detect interest points. Here's a whole bunch of them. The next question is how to match them. So I've got points in my left and points in my right. How do I find the match? To do that, I need what's called a descriptor. I need to describe each of those points by looking at the little region around it and look for that in the next image. And that's what we're going to do next lesson. Welcome back to Computer Vision. Today we're going to continue talking about features or interest points, interest point operators, key points. In particular, last time we talked, in fact, last couple times, we've talked a lot about how to find interest points, how to detect them. And we talked about the Harris operator and other kinds of ways of finding them. And here, for example, typical picture of finding interest points in two images. And so this is like about 500 points extracted with a Harris detector. And you can see that, well, there are a bunch of points found. And what's good is that a lot of points, like here on this turret here, is also found on this one there. So one of the things that we're looking for is, remember we talked about reliability, that points that you find on one should be found on the other. But now the question is, given that we found points in two images, image 1, image 2, image A, image B, alpha, bravo, pick your favorite, the question is, how do we match them? How do we determine which points in the left image are the same as points in the right, or multiple images? So to do this, we need what's referred to as a descriptor. A descriptor is a description of the neighborhood where the interest point is, and that's going to allow us to match. Now, we need a couple of properties of the descriptors, and what's important is that these properties sort of trade off. The first is that we want these descriptors to be what we call invariant. That is, they should be almost the same from one image to the next. And so why do I say almost? Wouldn't it be great if they were exactly the same? Well, it would be great if they're exactly the same, but also there were no duplicates. Remember that silly example I gave a couple lessons back, which maybe you just watched now, or maybe you watched 8 months ago, I have no idea, where I said, you know, if we name everything George, then it's easy to match them, except not really, because everybody matches perfectly, but you don't know which George is the right George. So the way we say that is we also want our descriptors to be distinctive. All right, distinctive means that one point, you know, some particular point here has the same, at the corresponding location, the other image has one descriptor, but a different point would have a different descriptor. And the reason that that's challenging is because these two images are a little bit different, it means even the same point, like the top of that Diet Coke cap that you guys can't see that Megan's been drinking because she drinks a lot of Diet Coke. Anyway, when I move a little bit, the image changes a little. So the neighborhood is not exactly the same anymore. So the descriptor is probably going to change a little bit, but we don't want to change so much that I can't tell that they're the same. But on the other hand, there's another cap nearby that I'd like it not to have the same descriptor so that they can be you know, unambiguously matched. So we have this trade-off between being invariant, found each time, and being distinctive. One is different from the next. So you might say, look, I've got a simple solution.
I've got a simple solution.
We know that the Harris detector gives pretty good detection, and remember we did that whole thing to talk about how to find the right scale, right? So we even know sort of the scale of the window. So why don't we just do this? Why don't we, for every feature we have here, we pick a window whose scale has been determined, and we'll just do correlation against all of the feature points over here using their appropriate scale, and then we just pick the best matches and we go through and do that all the way. That would be a great solution, right? Well, no. If it was, then I wouldn't be standing here telling you all this. So why isn't this so good? Well, first of all, just remembering about correlation, we have these two pictures, and we might have a different picture over here, a camera over here, and the features could have rotated. Right? And correlation is not rotation invariant at all. Remember we talked about how Harris detectors are very robust with respect to the rotation for detection, but to do the matching, we have to be robust with respect to rotation as well. Correlation also is pretty sensitive. If I made things brighter or dimmer, etc., I would actually change the values. So remember we introduced this thing called normalized correlation? Well, that's really not your savior either, because it senses some nonlinear changes, and actually very slight geometric distortions can cause your normalized correlation to get pretty bad. So if as I move and that bottle cap changes its appearance to me just a little bit, the normalized correlation could become problematic. And also this idea that I'm going to take one and I'm going to compare it against all of the others, and then the next one, all of the others, that would be very expensive. So we'd like to do something that's a lot smarter than that. So this lesson and the one next is about sort of essentially overcoming these problems. What I want to talk to you today is about what's called SIFT feature detection. SIFT stands for Scale Invariant Feature Transform. The motivation for the development of the SIFT transform, and this was done by David Lowe back 99 is really when the community first saw it, and then early 2000s. The Harris operator was not invariant to scale. Now we've fixed that later, and we talked about how to do scale stuff. And correlation was not invariant to rotation. So what David wanted to do is he wanted to do better matching, and he wanted to develop two things. One was an interest operator, a detector that was invariant to scale and rotation. And we talked about the SIFT detector last time, right? We talked about these finding the maxima of the difference of Gaussians both in scale and in space. And that by doing that you could determine the natural scale, or I should say the right scale. But the other part of SIFT was building a descriptor, that is the description of the neighborhood, that was robust with respect to variations corresponding to viewing conditions. So as you scaled the neighborhood, when you found the right scale, if you changed the brightness a little bit, as you rotated, and those kinds of things, to build a descriptor that would be robust under those transformations. And just inserting opinion here, for these days, for SIFT and things like SIFT, the descriptor is the part that's used most. Okay, that's the part that the idea of building these local descriptors was really significant and continues to be used today. So here's the idea of using SIFT for doing things like alignment or recognition of objects. And the idea is this. You're going to say that your image content, whatever your image is, you're going to transform that into a representation. The word I like to use is a constellation. I'll show you one in a minute. A constellation of local features, and that those feature descriptors will be invariant to translation, rotation, scale, and other sorts of imaging parameters. So if I take the object and I move it over and I get closer to it and I change the lighting, I would get the same descriptors. And so here's an example of shift descriptors. So you see here we've got a truck here, and it might take you a little while to in fact, here I'll show you. These are these little neighborhoods, all right? And these little arrows are just showing you these little neighborhoods. Okay, so we've got ones by the tires and by this thing, and back here by the logo. What might be a little harder for you to see is that we have the same truck right here. All right? And the point here is that a bunch of the same descriptors, so here's one and here's another, they were both found in the two images, right? And if I can find enough matches, then I can figure out, oh, this image has an object, and that object is also in this object. In this image, it's just been rotated, translated a little bit, maybe scaled. And that's the idea about using SIFT for doing the recognition. So if your descriptors were robust with respect to these transformations, you could find them from one image to the next. By the way, here's another description of the problem. This one also comes, I think, directly from the original paper or the second paper. You know, suppose you want to find this box of crisp almond cookies, because we always want to find boxes of crisp almond cookies, in this basket. And what's really interesting about this grocery basket is it has basmati rice, crisp almond cookies, and a computer vision textbook, because when you go to Publix, you always buy a computer vision textbook. Anyway, the idea is, can you find this box that's actually over here? All right? And the picture that's shown in the original paper, which is kind of cool, looks like this. All those cyan lines are the connection between SIFT descriptors found here and SIFT descriptors found here. This is the original image. this is the box located in the basket of groceries. So because it could find all those features, it was able to say, this object is really right over here. This was very impressive at the time. In fact, continues to be sort of a strong way of doing certain types of computer vision recognition. The overall SIFT procedure to recognition was originally defined to have sort of 4 components. The first 2 were finding these extrema, those are those maximums of difference of Gaussians that we looked at, and to detect, localize exactly where they were. So these days, as I mentioned this before, a lot of people use the Harris-Laplace method of doing this instead, where you do Laplace in scale and Harris in space. Whatever it is, use some method to find your key points and also to determine the scale of the key points in the image. Then what you have to do, there are 2 more things related to SIFT, and we're going to do them today. The first is we're going to define an orientation. That is, we don't know how the image has been transformed, and of our little local neighborhood, we want to know what the orientation is. And then, once we have an orientation, we can think of that feature with respect to that orientation and build a descriptor. And by the way, I'm using the phrase here key point. Key point was the terminology used in SIFT. What we're talking about is these detected interest points, and you're going to use them as key points, you're going to use them as features. Key point description is the descriptor we're going to use. All right, here's a picture taken out of, again, the original SIFT work. Here's just a small image of a house on the left. And what this incredibly ugly graphic on the right is just, and we've got better ones in a minute, but this was the original, is just there were all these little key points, and you can see these direction arrows, okay? And those directions are going to be the little local orientation that we're talking about. So let's talk about the orientation assignment, computing the best orientation, okay? Well, that's actually pretty easy. Remember the gradient, and we have different operators for doing the gradients. So what we're going to do is we're going to compute the image gradient at all these points, and then locally we're going to compute some estimate of orientation. And the way we do that is really pretty simple. So nominally, this is your image area with a little line drawing in it, just shown here. But the idea is you're going to build a histogram. Okay, this is our little histogram, where you've cut the angle of orientation into some number of bins. In this particular case, they were using 36 bins of orientation. What's the right number to use is a question. All right? And then what you do is you say, I've got a peak, and I'm going to say, okay, that peak, that's my dominant orientation. And that's going to be the orientation that we use. Okay? Once we've picked that, that becomes essentially our new north. Okay? We're saying that's the way we're going to think about our window here. Now, once we've done that, notice we've found it in XY, so we've removed the translation problem. That is, we know where it is. We found it in scale when we detected the interest point to begin with. We picked the scale, and now we have a new orientation. So what that means is that whatever descriptors we build are going to be invariant to the transformation in X, in Y, in scale, and in orientation, and that's what we wanted.
Here's the dolphin image we've seen before. Let's say our interest point detector found this tip of the fin to be a possible key point. We zoom in on a 5x5 neighborhood around the key point. Now recall how you computed image gradients, say using a 3x3 filter. When we place it over this pixel, what is the dominant orientation you see? Right, it's along the diagonal going towards the top left. Let's use this approach to mark image gradient directions for other pixels. To avoid edge conditions, we only consider locations where the filter fits inside the image patch. Also, we approximate or quantize to 8 directions, vertical, horizontal, and diagonals. Can you figure out the dominant orientation of this patch using the image gradient directions? Select the appropriate radio button. Alright, you might be able to tell just by looking at the arrows. But what's the proper way of doing this? Yes, let's build a histogram. We create 8 bins, one for each possible direction, and then start counting how many go in each. For instance, our first arrow is towards the top left. That goes in here. Okay, how about the next one? Same bin. That's pointing up, and so on. Notice that there is no clear winner. So what do we do? Remember that we need to smooth the gradient histogram. At this level of detail and quantization, each pixel's contribution has a significant effect on the overall histogram. Therefore, we need to soften these contributions, which can be done by smoothing. We see a small bump here, and then a much larger region that wraps around the direction axis. Notice that anything going past the end resumes at the beginning. Okay, now we can locate our peak. It's at the arrow pointing left, and this is our dominant orientation. Pointing left becomes our canonical north, and all the other directions are recomputed relative to it. Our shifted histogram would look something like this. This is the basic idea behind creating rotation invariant feature descriptors.
So now the question is, we need to compute this descriptor about this local image region. All right? And remember, we want two things for a descriptor. We want it to be highly distinctive, that is, given two different points in the image, I should come up with two different descriptions. But we like it to be invariant as much as possible to small changes in viewpoint, maybe even large changes in viewpoint, illumination, and other kinds of imaging parameters. So before we build that descriptor, we normalize. What's the normalization? Wherever our little window is, we're going to say, okay, this is our new north. We're going to rotate north to be up, let's say. So we're going to rotate them all back. And the other thing is we're going to scale it to be some uniform size. So when we did the detection to begin with, it said it was a small scale, we're going to blow it up to be that size. And if it said it was a large scale, we might shrink it down to be some fixed size. So the idea is that we pick particular size. By the way, getting SIFT to work is painful. And that's one of the reasons people tend to use libraries for descriptors. Because there's a lot of, the expression, the devil's in the detail. There are a lot of details to making this work. So here's how we're going to build our descriptor. We're going to build a feature vector. So there's going to be some vector of some length, okay? And it's going to be based essentially upon properties of the histograms of gradients. All right. So what I'm showing you here is, this is a nice picture. Nominally, this is pretending that we've got a little grid of 8 by 8 pixels. I'm only showing 8 by 8 because to show you more would be too hard. Okay. And what we're going to do is we're going to take this histogram of gradients. All right. And we're also going to weight it by a Gaussian. So sort of this circle that's drawn down here, and there'll be circles, right? The idea is that we're going to, if our center point was located in the middle, we're going to take the gradients in the middle to be weighted more than the gradients towards the outside. So what we're going to do is we're going to build these little histograms. What we do is we take, say, 4 pixels by 4 pixels. Can I count to 4? Yes, I can. Okay. And we take a little histogram of those orientations, and that's done right over here. So this thing has sort of 8 different dimensions. And then this 4 pixels here would be there. Now, I'm only showing this as a 2 by 2, right? 1, 2. Well, actually, for real SIFT, they do a 4 by 4. 2 by 2 just shows better. So just to think about that, we have a 4 by 4 array. That's 4 times 4, that's 16. Each histogram has 8 bins, so that's 16 times 8, that's 128. That's 128 numbers, okay? Those 128 numbers, that's the feature vector that we're going to use to describe this, this single key point. This is the descriptor that we're going to use. Because you take these 4 by 4, now I'm going to try to draw them out, and it won't look quite so good, but you'll see what I'm talking about. Okay, so I have 16 different little histograms. Because I stack them up into a feature vector, I don't add them together, I stack them into a feature vector, there is a certain amount of spatial sensitivity, right? The top left hand, let's suppose the top left hand histogram is the first part of the feature vector, right? All the way down to the second, the third, the fourth, finally the last part on the bottom. So there's a certain amount of sensitivity to the spatial layout. Right? So if you've got some orientation of gradient in the top left-hand corner and different on the bottom right-hand corner, you get that spatial layout. But it's not a very strong sensitivity to the spatial layout, which is good because that maintains a bunch of our viewpoint invariance. And remember, we have unrotated this thing with respect to the dominant orientation locally. Okay? So all of our histograms that are being put down are placed with respect to this normalized orientation and scale. So now we have this 128 vector. And also remember, we've been smoothing by these Gaussians, so the middle has more weight. In fact, and I mentioned this before, in order to make these things work, we ensure smoothness. In fact, I think in David Lowe's work, they originally talked about sort of trilinear interpolation. What they meant was that points get smooth, and they contribute not only to bins, they actually overlap the histogram bins a little bit. And that way, each pixel corresponds multiple times, is used multiple times in different gradients. And also, they vote into adjacent orientations. The details don't matter so much, but what it means is that if you get a small shift in where this neighborhood of 8 by 8 or 16 by 16 pixels land, you don't get a large change in the descriptor. And that's really important because when you relocalize a point from one image to the next, you're not going to land, you may not land in exactly the same spot. So this smoothness allows you to get a very slow change in the descriptor as you move just a little bit, and that's really important. This also is why I said it takes effort to make these SIFT libraries function. One of the things you don't want to do is, remember the magnitude of the gradient. I'm not sure I said this, that it's weighted by the gradient. It's actually a weighted magnitude gets used in the histogram. Well, a problem with that is if something has very high magnitude, it's going to dominate the votes, or it's going to dominate the descriptor in a way that you might not like. And so one of the things that they advocate doing is after you unrotate, you normalize the rotation, clip the magnitude of the gradient to some maximum. Okay, so you don't let it get more than a certain amount. He talks here about 0.2. Which one you use is a function of your own imagery, but the idea is that it gets clipped. The second thing that you do in order to prevent any sort of illumination change from really harming you is that you take this 128 long vector and you normalize it to be magnitude 1. And that way, if more gradient vectors show up because you've scaled everything, essentially things are better behaved because you're going to be comparing these descriptors one to another, and you want them to be sort of a similar magnitude. So by normalizing them to 1, they're all exactly the same magnitude, and it's just the distribution within that vector that gets used to compare them. I suspect that has a function of exactly how you did the comparison. If you were doing dot product kinds of things, the magnitude normalization might matter a little bit less. One of the really nice things about some of this initial work is they did some pretty extensive evaluation. They would take a whole bunch of images and they would they would rotate them, they would scale them, stretch them, change the brightness, contrast, and add noise. And then the feature point descriptors would get run on the original image and the transformed, the distorted image. And then what you could do is you could say, under some matching criteria, how often does this descriptor, how often is its best match in this whole other image the correct one? The correct one being actually comes from the same point on the same object in two different images. And that's what they evaluated. So here's the first graph that I'll show you. Again, the error measure is the correct nearest descriptor percentage. How often is the one that matches best the correct one? All right? And then they varied a couple of things. The first thing that's easiest to see here is this number n. This was the number of those of the histogram that get used. Remember I said I was showing you only a 2 by 2, but they actually used a 4 by 4. Well, one of the reasons they used a 4 by 4 is a 2 by 2 is here, a 3 by 3 is there, a 4 by 4 is here, and all of a sudden you're sort of maxing out. So it looked like 4 by 4 was a good thing to use. By the way, this was evaluated by looking at a bunch of images and 40,000 key point descriptors, a bunch of images. So they looked at 40,000 different descriptors and the corresponding other image with all those perturbations. And so it's pretty serious evaluation. The other thing that's shown here is how many orientations in the bins, right? How many orientations in the histogram, how many bins? So you could have used just 4. You could have used 8, you could have used 16. Well, what you can see here is 4 does that. When you go up to 8, it gets much better. When you went to 16, you didn't do very much better than 8. So they picked 8. All right, so this was an empirically motivated set of parameters. Without going into too much detail, they also show this is as they add image noise to the picture, how much percentage of pixels get noise or the magnitude of the noise. And you can see that the correctly matched value, again, falls off nice and gracefully, which is what you're looking for. You're looking for it slowly. By the way, going back to this previous one, you know, it's only getting up to like 50% match. We don't need everything to be matched correctly. We need enough of them to be matched correctly. And we'll assume the ones that don't match are all voting for Santa Claus, Mickey Mouse, and Donald Duck, if you remember that analogy, right? The ones that don't match sort of arbitrarily. So as long as we get ones that match well, then we're doing okay. Here's a very nice table of some experimental results. Just shows you the different kinds of perturbations that they did. Okay, and they're talking about different ways of comparing the matches, about whether you just, you know, do you get the right location and scale, and what about orientation. The thing that really matters is that you're doing all these different things. You're looking at changes in intensities, rotations, scaling, stretching, 10% noise, and you can see if you do all of those things, depending upon whether you're looking at just location, scale, or including orientation, you still get above a 70% match. And that's pretty remarkable. In fact, there's a nice figure that comes from here. So here's an original image, and drawn on top of this picture. In fact, you can almost not see the picture underneath. There are all these feature points, okay? And what they did is they took the picture and they rotated it 15 degrees. They scaled it down 90%. They stretched it 10%. Okay, an extra 10%. They changed the brightness down by 10%, changed the contrast, multiplied it, and they added some noise. And then they went back and they took a look at all their feature points. And how well did it match? Well, I love this little animation. See, the whole thing flies in here, and it says 78%. That's pretty cool. What that's showing you is that you have this very robust descriptor, and yet it's distinctive enough that you can find the correct matches. Here's another example, again, from the paper. What you're looking for are these little things, okay? So this is a little piece of the house. This is a little piece of the totem pole. This is something else that was on the totem pole. In fact, it's a little hard to see, so I put these little colored dots. So we're looking for these patches over here. What you're going to do is you're going to create little sift features on all these things, and you're going to look for those patches in the corresponding image, and what are you going to find? Voila! Basically, the thing works. Which is not a surprise. It came from the paper where they're claiming it. By the way, SIFT is actually intellectual property owned by the University of British Columbia. So before you go implement it and put it in your iPhone in order to do something clear, make sure you hire a really good lawyer. That ends this lesson on SIFT descriptors. As I mentioned, getting SIFT to work can be painful, and that's why those of you who are taking the OMS version of this and working on a problem set using it, we'll be giving you some libraries for computing the descriptors. You're going to be on your own for finding the points, finding the interest points, and figuring out maybe the scale, or maybe we'll just fix the scale. But the idea is that then you can use the library for do the descriptor. Then you're going to have to do all this matching, okay? Now, you know, matching, if you think about that, suppose you've got 1,000 descriptors here and 1,000 descriptors there, right? That's 1,000,000 combinations if you're just trying to compare this one to each point here to every point there. If you've got 10,000, that's 100 million. That might not be really a very good idea, so you might want to do something smarter. And what would it be to do smarter? What would be really smart would be to watch the next lesson so you could learn how to amaze your friends doing this. Welcome back again to Computer Vision. Today we're going to continue a little bit on, we did SIFT feature descriptors last time, and descriptors in general, and today we're going to talk about matching them. We're only going to talk a little bit about matching, because actually there's only a little bit you need to hear. So, okay, so where are we? We know how to detect points, right? So we detect feature points. And we now know how to describe them. This little notional picture here showing you that we can build little feature descriptions using the SIFT method that we talked about, where you get a 128 long vector as a descriptor for each one of them. So now the question is, how do we go about matching them? Which is kind of a sneak here, because I started off with this slide last time that said we're going to do matching, and we didn't do the matching, we just did the descriptor. I'm not even going to tell you about matching again. I'm going to tell you about how to search for a match this time. So we already said that you could just do nearest neighbor, right? I get a point here, key point here, I search every key point over there to find out which one is best. And by the way, as I mentioned before, those of you doing the problem set will probably end up doing just this. But as we pointed out, that can be really expensive. You might have thousands of points here and thousands there, and that's an awful lot of combinations. So we're going to do something a little bit smarter, okay? We're going to use an approximation to a nearest neighbor search. And the idea is that we generate hypotheses from an approximate nearest neighbor matching for each of the vectors. And it's essentially, SIFT uses this algorithm by Basin Low called best bin. And it's a modification to the KD tree algorithm. And I'm going to assume those of you who are in computer science that you have some familiarity with what KD trees are. It's essentially, you can think of it as, in a binary world, just binary splitting things. K stands for K-dimensional tree, where you split them along. It allows you to access points in essentially a log n instead of something proportional to n. And they did a little modification of that allowed you to sort of sort your bins that you're searching for quickly. And 2 points are important about this. One is that it is a pretty good algorithm for the SIFT search, and it's reported anywhere from 2 to 3 orders of magnitude speed up. And anytime you can buy 2 or 3 orders of magnitude speed up, you should do that. Now, of course, you can't cheat the piper. Nearest neighbor is a certain algorithmic complexity. By doing it this way, you find the nearest neighbor, the one that actually matters, on approximately, again, empirically, they'll tell you 95% of the time. So you have to wonder, exactly where it is. It can't be guaranteed, but the idea is that for sort of well-behaved systems, you're getting in the 90-plus percentile. Which is good, because if you remember before, we said the descriptors aren't perfect anyway. So some of our matches are going to just be wrong. So if we're finding 95% of the right matches, that's going to be pretty good. This figure here sort of shows you a little bit what's going on. Again, this comes from their paper. The algorithm was called best bin first. The idea is if this was your probe point and you found this point D, when you do normal KD trees, you essentially recurse up the trees and branch out looking for nearest points. And all that they did is they had a way of sorting through the bins. So they would order the bins themselves so that you didn't just recurse through the tree. And it gave them this speed up. This listed here is the reference to the paper. And it just makes it easier to find the nearest neighbors, to usually find the nearest neighbors. Another cool thing you can do is do some form of a hashing-based method in order to index. So what I'm showing you here is what's called wavelet-based hashing, done by Brown, Sliski, and Winder in 2005. Comes from Sliski's book. You can see it. And basically the idea is this. So here's our little neighborhood. Okay, and we apply what are called these hard wavelets. Now, wavelets are just a self-similar form of filters. They can be applied at different scales. We didn't talk too much about them. That's okay. But basically, these are the 3 filters, and these filters are, sum up plus here, minus there, plus here, minus there, and then plus here, minus there, minus there. Okay, so what you do is that means you'll get 3 different numbers, right, from each of the 3 filter outputs. And what you do is you can then quantize each of those into 10 bins, or maybe 10 overlapping bins. All right? So if you have 10 bins, 3, that means you have 10 to the 3 different possible values that you can get out for a single application to the neighborhood. And because the bins overlap, you don't have to worry about, well, maybe I got out a 4 versus a 4.1 for some value, because the bins don't have a sharp border, they have an overlapping border. So then what you do is you compute these 3 numbers quantized to over 10. That gives you 10 to the 3 possible bins to pick from, and you go and you get that. So that reduces the set of neighbors that you have to look at, or the set of key points you have to look at, by a factor of something less than 1,000 because of overlapping bins, but between 2 and 3 orders of magnitude. Pretty cool. This is related to the general idea of what's called locality-sensitive hashing. All right? So I'm going to assume that most of you as computer science students, you know what hash tables are and what hash functions are, and if you don't, you may not understand this. Normally, a hash function maps some data structure into some nicely distributed space. So you might have a function that maps structure to the integers between 1 to 100. Okay, and you can think of those integers as bins. So if you give me some new data structure and I want to know, have I already seen one of these before, I map it through that function and I go and I look at the bin and I only search through the ones that are in that bin. Okay, so if it's distributed kind of evenly, you're going to reduce your search work by a factor of 100. Right, because you apply this function and you reduce it down. But the problem with the design of hash functions is that they are very precise. They're designed for precise data structures. Locality sensitive hashing works similarly, but it's a little bit different because it takes the notion of distance into account. And the basic idea is you're going to construct some hash function. Here it's written as g, okay, and it's going to map onto some output u. All right, and the idea is, and there's some like Greek written here, etc. But the basic idea is that if you have 2 points that are nearby in the original space by some distance measure, then the probability that those 2 points will land in the same bin should be pretty high. Likewise, if I've got 2 other points that are far away in the original space, the likelihood that they land in the same bin should be relatively low. Okay, that's what locality-sensitive hashing is. And when you do that, it means that I can compute this hash function, go to whatever bin it sends me, and the idea is that descriptors that were similar, not exactly the same, but similar, will be in the same bin. There was some nice work done by Kulis and Grauman. The title is Kernelized Locality-Sensitive Hashing for Scalable Image Search. There's a lot of work on kernel functions. We'll talk about them later. This is not the kernel of a filter. Sorry, they use the same name. But the kernel functions here are a way of mapping from some dimension to some higher dimension and then operating on them. And this is an approach of how to do applying these kernels to SIFT features. What's important is it's a nice discussion in there about doing this locality-sensitive hashing. So to wrap up, let's talk a little bit about doing some recognition using our SIFT features. So basically, at training time, I give you some object. You somehow have to get hold of just that object in the image. Okay, so what's the easiest way? Well, you put it against a black background. Okay, so you find the outline. Everything inside there is the object, and you compute your key points. You find your little SIFT descriptors located all over the object. And in here, you find these outlines, okay, but again, there would be little SIFT features all over them. The outlines are what we're going to overlay when we say that we found the image, okay? So at test time, what do? Well, we take the key points from our test image, and we compare each one of them against, let's suppose we're looking for, I don't know, telephones. So we take the key points of the telephone, we try to find the best one that matches, exhaustive nearest neighbor, best bin first, locally sensitive hashing, whatever it is, I try to find the best one, and I compare a whole bunch of them. Here comes the trick. Now I want to find a consistent set of matches, okay? So what that means is I'm going to do the following. Let's suppose that I believe that the difference between this picture and that picture is an affine transform. Okay, now you're scratching your head to try to remember that whole affine transform thing, because I'm about to ask you a really hard question. How many pairs of corresponding points do I need for an affine transform? The answer is not 4. 4 was a homography. 1 for translation. 2 is similarity, translation, rotation, scale. It was 3 for an affine. So an affine will let you do a translation, rotation, scale, and a shear. So if I find 3 good points here and 3 good points there, that allows me to compute my affine transform. So then what I could do is that tells me where every point from the left image should appear in the right image. So I could now check to see if I take all my key points from my teddy bear, do they all land at matching key points when I apply that same affine transform? Okay. We'll actually spend a lot more time talking about how to search for transforms over matches on the next lesson. But for now, you can just think about doing it sort of this brute force way. So how well does it work? Well, here's a nice example of finding both the telephone and the shoe. So here is the original phone, and here you can see the outline. And here are the modest number, I don't know, about 15 key points that have been matched. Now remember, you only need 3 to find the affine, so by finding more than 3, you get a much more robust solution to the transform. Likewise, see, so here we have our green shoe, and here you can see where it's found. And again, you can find the set of feature points, key points that were matched. What's also pretty cool, I only need to find 3 points from one object in the corresponding place, and then I can predict where the rest of them go. So that means I don't have to see the whole object. So here you see an example. Here's the shoe. I'm going to draw inside so you can see this, right? But you'll notice it's being occluded by this box of whatever the groceries are, okay? Only the front part and the back part of the shoe were found, all right? But I only needed 3 matches to find an affine transform, so I didn't have to see the whole shoe. I only had to see enough of it to do what's called the alignment. Same thing is true of this telephone here. The whole back end of the telephone is missing, but we're able to recognize it by just finding features within the front part. That's pretty impressive robustness with respect to occlusion. Here's another one. Now you can see again, David had this thing about teddy bear shoes and telephones. I'm not exactly sure why. Anyway, here you can see the shoe is behind the teddy bear, and only the front part of it is visible, but you can see it. Same thing with the phone. So the idea is that as long as I can find a small number of these local matches, I'm able to do the recognition. Oh, and here's one you saw before. Remember the totem poles? He's at UBC, University of British Columbia. They got a lot of Native American Indian stuff up there, so I'm guessing that's what this is. And you remember the thing just works. There was a more recent application of SIFT, very explicit. You guys, I don't know how old you are anymore, but maybe you remember the Sony Aibos, the dogs that used to go around and would recharge themselves and live in your house. It was sort of an experiment that Sony did for a while. It was kind of successful, but eventually they stopped making them because I think they were learning from it and moving from there. Well, one of the things that the dog could do, well, there were 2 things. It could recharge itself, and you could show it cards, and it would do the commandment based upon what was drawn on the card, what was printed on the card. And the way it did that was using SIFT features. All right? So the charging station had a pattern on it, and as the dog walked around and just did kind of whatever it did, whatever little robot dogs do, it would see this pattern. It would be oriented, it would be translated off to the side somewhere at a different scale. But remember, SIFT is translation, rotation, scale, and variant. So it could find the charging station. Also, they had these what were called visual cards, and they were things like this. And it doesn't really matter at all what's on the cards. As long as they have gradients distributed all over them, the dog can recognize which card you're showing it. You know, I said it doesn't matter at all what's on it. It does matter a little. It has to not look like anything the dog would see otherwise. So if you wonder why do these cards look so strange, it's because it can't look like my dining room table. Because if it looks like my dining room table, my dog will see my dining room table and roll over and play dead or whatever robot dogs do. So that ends this lesson on finding matches for SIFT descriptors. And it's really, all I've really talked about was some clever indexing and hashing methods that have made it much more effective as a way of describing and finding matches. As I said earlier, if you had a really fast computer, you might just do full nearest neighbor. Or if you had all day to do a problem set, you might just do nearest neighbor. But if you actually have a real-time device that needs to do something a little more clever, then you need something that accelerates that pace. Going forward, what we're going to talk about is to use a small number of local matches to determine a best global solution. Now, this should remind you of something we've done before where we take sort of a modest number of local events and find a global solution. Remember that whole voting thing? Well, what we're going to show you is another way that's more appropriate for doing things like I've got some SIFT features. Some of the matches are good, some are not so good. I'd like to find the best global match. What's the way of doing that? And we'll talk about that the next times.